Alright, you guys, it looks like we're live. So we're not going to start for another 20 minutes. Just letting you know. You guys hear me? Yeah, there were almost 200 RSVPs for this event. So I'm hoping 100 people will be here. There's enough chairs for 100. But I'm going to live stream. I'm live streaming right now.
Great. I posted that on
So yeah, so that URL is now live. I usually start a little while. I already told you earlier. So I usually start early, and then the numbers will go up, and by the time the event starts, we'll have 20% people on. The last time I did this at a meetup here, it went really well. There was probably 20-something people watching live. It's good numbers.
Is there any problem in you taking photos or anything like that? For social media?
Yeah. Yeah, I use my third handle. Sorry, what was your first name? Jennifer. Nice to meet you.
Hello. Nani? I'm Vince. Hi, Vince. What do you do? Add intelligence to the very edge of the digital world.
That's a very best place to be.
Sensors and actuators.
Sensors and actuators.
Yeah.
What sort of sensors and actuators?
We're more focused on basically adding the compute resource to the sensors and actuators.
Here's the mic mark. It's the only thing I'm using in here. It's all I got today, but it's pretty good, and I think the speakers are mic'd. So.
The general idea is to have a platform that goes across penetrating the sensors.
I'm working on the
Oh, okay.
I see that you're taking the
Oh, yeah, I just seen what they were teaching. We're a little startup. We're about 3 years old. We're self-funded so far. It is. So we're 90 people. So we probably actually won't, well, we'll never manufacture this. But also part of it is the infrastructure to manage this distributed software out to that very far edge and manage it, make sure it's encrypted and
This is Ravi.
Ravi?
Nice to meet you.
Nice to meet you too.
And Vipin should be here shortly. He'll be our MC.
Okay, great. Hey, what can I get about?
It's very general.
Bottle of water. I'll get you.
It's primarily focused on adding
Alright, so are you faculty here at the school?
Yeah.
What kind of courses do you teach?
I teach two courses. One is advanced microprogramming. Title is called microprogramers. And the other one is deep learning.
Nice.
The deep learning one I'm going to start. This is my last time.
Yeah.
I took a new job and the job is more effort, so I want to focus on the job.
Is it a deep learning job?
Yes, it's machine learning deep learning job with data pipeline for computer vision application.
Interesting. Well, congratulations.
Thank you.
Yeah, I'm looking forward to hearing your talk.
Oh, cool. Yeah, same with you as well.
I'm gonna be talking a lot about brains. I mean, that's what all we focus on.
Okay.
But it should be
So
interesting.
you guys focus on the biology side of things?
Yeah. Well, the theory. So we understand the biology, and then theorize about how the circuits
The
are.
mathematical.
Not so much the math.
Okay.
The neural circuits. I'll explain
Oh, okay.
a bit more.
Okay, interesting.
But I mean, my company's been around since 2005. We started doing Bayesian networks and Bayesian modeling, trying to apply them to the brain, the whole Bayesian brain idea. And we ended up throwing all the Bayesian stuff out and going to the neurons and the circuits within different, like, specific layers of cortex and trying to understand from a temporal standpoint over time, how can we model specifically what the neurons are doing? So that's really what we focus on. It's something you can't really do with a perceptron unless you use a network to model the neuron, you know, and that's really efficient.
Okay. So, do you guys work with images of neurons, or how do you understand? How
Images of neurons?
Yeah.
Well, we follow neuroscience research pretty closely.
Okay.
We
So there's
read
kind of
experimental neuroscience
kind of
papers, and yeah, we're specifically interested in, you know, the computational power of a neuron. What's it doing, and how do they work together to represent semantic information, and how does that, you know, flow from one part of the brain to another part of the brain?
Okay.
Like our big questions right now are, how do we model objects? You know, it's just a big question. And I'll talk about that.
Interesting. Sounds very different from all the stuff.
It's very different than.
I'm from the imaging background.
Yeah.
So the company where I work for, we do imaging of tissues. Our
Oh, like
resolution.
neural imaging or biological imaging?
Any
type
biological
of
imaging. Any biological imaging. Oh, thank you.
I used to do some satellite imagery work a long time ago.
So we do acquire images for, we sell machines, plus we also acquire images for pharmaceutical companies. And we recently acquired images of paper fields. So each field of view is like something like 500
absolutely.
microns.
Microns.
5 microns.
Yeah.
And we acquired a tile of like 50 by 50 or something like that.
Yeah. Yeah, that's interesting. There's some really beautiful visuals that comes from imaging neurons and staining them and seeing where they all go. Yeah, it's very interesting. So some of our theory comes from hippocampus. So I won't talk specifically about hippocampus today, but I can talk about it to you later. Hippocampus is super interesting, part of the brain. But we use, like, things we've learned that happen in the hippocampus, we think also happen in other parts of the cortex, like isocortex, entorhinal cortex. There's this representation of location in the brain that seems to be really important. And we think that's used as sort of a primitive part of all object representations, like space is at the core involved in all object representations. Like somehow the way we understand space, the way we explore space as babies with our senses, we use that to understand everything. At least that's what it looks like in the neural representations.
Not worried about it yet?
We're not worried about it yet. It's, I mean, pure research, really. Pure research. Well, so here's how we do image processing. Here's how, I mean, you have to move. That's the thing. Convolution's not enough, at least in the brainwave movement. You have to move. There's no intelligence without some form of agency or some form of movement, an environment or a substrate that changes your point of view, like the point of view of the sensor. Because that allows you to explore. So that allows you to say, when I take action, things change, and if I can keep track of that, I can keep track of how my actions change things, right? that's really core to the like
Oh, yeah,
intelligence theory
absolutely.
and
If you have one
brains.
of ours, it's-
So that's what Numenta is.
Should be an interesting topic.
Thank you.
A lot of new information.
Yeah.
So
think I
you
got
have
it.
a PhD in biology or something like that?
No, I don't. I'm a software engineer by trade.
So we host
So I've worked in industry on the jet brain. I actually started in military defense contracting stuff. Went into just for software engineering for several years. I got out and then got hired at Yahoo. I worked there for a couple years, and then got hired. I've worked at Numenta for 8 years now. I started as an engineer and worked up to a manager of our web service platform, and then took over when we made our code open source. I took over as the community manager, so I do all of our sort of public-facing, community-based work, community outreach, tutorials, a lot of technical things too. So.
How are you? Good to see you again. Yeah, looks like record sign up.
I hope they all show, or half of them show.
Becoming very celebrities.
Thank you. I think I might have some part.
How is the classes going? Are you still active in machine learning?
Yeah.
The
I'm
deep
deep learning
deep
class,
learning.
but this is the last term. I'll be teaching deep learning. It's a new job, and for a new job I need to learn.
So where are you from?
I'll be back in November, end of
Residents also.
No, we'll look still in Santa Clara. Yeah. The computer service take like 1 hour back. It's like what used to be like 20 minutes. That's another one. That's why I decided to move.
Yeah, I think it's a good change.
Exactly.
Hoping to hear more exciting things from you.
We have a solstice tree.
And it's called a company called Numenta.
Yes. We've been around since 2005. So our primary mission is to try and understand how intelligence works in the brain. So biological engineering. So, it's a hard problem. But I think we really have made strides in understanding how it works, and I'll talk about it.
Because
I'd like to speak to that separately because I won't be able to sit through the whole presentation
not
today.
quite bonfire.
But I know
I
that
just stepped in because my
I want to met my brother.
it's actually a protection I was planning to leave, but it'd be definitely good for us to connect because I work in the
Conifers are obviously
the
solstice celebrations.
this is a
Right.
It's a conifer, but it's the only native conifer
we
that's
would
on the
have the
Pacific.
way the human brain works.
Yes.
So you are having kids, family, they have
It's even GPU architecture.
Norfolk
Yeah,
Island
very
is-
different.
Norfolk
I
Island
mentioned
is
that today. I think that the way forward with this is sparsity.
Although we have results with
There's a next wave of chips that's going to hit the market
So-
3 to 5 years. That's going to be
Right,
a big
yeah, I mean,
deal.
it's native to Norfolk
And then
Island.
the other big thing that I tell everyone is the next biggest innovation in AI is going to be in the chips.
Yeah, absolutely.
Because after it's going to be
Okay.
Yeah. Well, even on GPUs right now, we're sort of maxed out. That's why
It's sort of like Hawaii.
you have to make algorithmic changes to make your dense network sparse. So that's what we're actually working on. Numenta is everything you learn about the brain when you look at sparse. It's like representations are distributed and sparse, and that sparsity gives you these properties that are really important for intelligence, like noise tolerance and fault tolerance, and generalizations in general. Like one semantic pattern, if it looks similar to another pattern, it is similar. So that applying sparsity, there's a certain way the brain does it. It gives like a bunch of sensory input and super active, and it just swells it down, right? It makes it sparse. So we understand how that works. And we're rewiring convolutional neural networks to make them sparse. So you can easily take like a standard architecture and say, let's turn this into a sparse architecture. And you get the very similar results, much fewer weights, since you get sparse weights, sparse activations, and then you've got much less training time, and much less compute, and smaller models, and
because
but traditional hardware to make it really hit, you need that hardware.
But I keep telling there's no point in even if you're on a train, a chair, picture of the chair, you don't need million chairs. A baby when it gets up, right? Mom and dad points in one chair. You don't have to keep saying that's a chair, this is a chair.
There's nothing intelligent hasn't learned to move. The only way we know intelligent things can learn
Mild,
is through
brandy,
movement.
chocolate,
And that's
alcohol.
completely
And then of course you're being,
reinforcement learning. That incorporates
and then actually, so I evolved the rest of
they're
my
already
years.
disassociated with reality.
Partly
You have to build up the model of reality through movement. And that's
actually,
That's a key point. Since I won't be around for the next
it is used.
Yeah.
Sharing it. All the really ingredients.
I've already tested my iPad, so everything works.
So you get here for another one? Yeah, I'll be here.
So it's just sort of funny, I'm running this customized.
So you just come back to
There are 33
remember
people
what they're
watching.
supposed to ask us.
Hey, thanks for joining, everybody. There's 33 people online.
He's going to give an amazing talk, a very different talk. Nobody wants to ask him.
We'll
It's
see.
going to be completely different because
see.
hardly people here discuss biology in this campus. Oh yeah, I know.
Deep learning is here to stay.
For a while, right?
It's somewhat overhyped, but it's not that overhyped. There is some.
It won't lead to AGI, but
Yeah,
there's still
exactly.
lots of money to be made. We can do a lot of things.
Yeah.
You can push that narrowness into a whole bunch of corners individually and do amazing things, for sure.
In fact, when new Java is joined, they already have some code built or some yeah. In the middle of some computation, suddenly there's machine learning. It's not something you used to see before, like 10 years ago.
Yeah.
Machine learning used to be a separate thing.
Yeah.
It's like in the middle of computation, you have machine learning.
Yeah.
And then more computation, another machine. Whoa.
Yeah.
This is different.
Well, there's a lot of companies are putting together case studies of how machine learning helps it, and they apply it to things that no one would ever apply machine learning to.
Yeah,
You know, there are so many simpler ways to do that.
Yeah, that's the interesting thing. Everybody comes to us and asks, can you give us some ideas whether we can apply machine learning to what we do?
Listen, if you don't have that problem, don't get involved in that problem.
The rule-based
We have two
engine,
problems.
rule-based engine works anyway.
In fact, I just switched a shot not just team, but something else. They're saying that if you're building a system, first build a rule-based system. If you can code a rule-based system, then you learn
Absolutely. And that can get you
And if it
80%
doesn't-
of the way on most everything.
Yeah, exactly.
That's something, all those people are scratching their head at. So many POCs are failing because of that. But they can be well done using a rule-based engine. Now they're doing POC of machine learning. That's the beginning and end of it. So Ravi, have you worked on this vapor images? Semiconductor, not really medical imaging.
Medical is what I've done mostly, but if there's something new, I
Because
don't mind
we're
talking.
looking at some high company detection.
I don't think I'm gonna have a better solution for the slides, you guys. I'll just put it on the other camera so you can get the wide view. But there's just not a good place in this room to put a camera close to there. So this is the best you're gonna get. I'll make my slides available. I'll ask Ravi to do the same.
It's an image that's very small.
Just to talk about
You can talk about it.
So just text me when you have time. Sure. Is she even expected for you?
So much information. But then they do start saying that this one.
Well, the example that I give you, AI analyzes situations.
But that's a new way.
Ravi, are you willing to share your slide deck with the watchers? Yeah, I have your email, so I'll ask you about it, and I'll probably post it with the video.
And then they also start shadowing the document.
Billion
Data points, you know, on number of bits.
means that decisions are not this is why
Anytime.
Now, starting this term.
well,
But there are a lot of
most of the ultimately it's going back to tweaking those and calculate expected pace.
so that can be research, clinical observation,
I'm testing different mic setups, just say. Check, test.
campus.
Try different ones when they start talking.
Hey there.
Hi.
You live casting it?
Yeah,
Cool.
I'm Matt.
Dale,
Nice to meet you.
nice to meet you. You're the AV guy or?
Well, no, I'm giving the second presentation tonight.
Oh, okay.
And I dabbled in live streaming, so I thought I'll stream it. There's 32 people watching right now.
Awesome. I noticed you had a Lex Friedman podcast.
Oh yeah, my boss Jeff Hawkins was on there. Did you see it?
Not yet. I just noticed.
It's a great interview.
I listened to Lex Friedman podcast. Didn't catch that one. When was it?
A few months back. Yeah, it was great. I was really happy to see it. When he started doing the machine learning interviews like a few years ago, I was so mad because I was like, why? Please ask Jeff, because we're always talking about what the brain can teach us about, AI, and so eventually he got it. So that was exciting. And it's a good interview too. It's one of his best. Probably his best interview.
And community manager, what kind of community do you
Well, it was started as an open source software community. Now it's sort of a theory community. You know, we still have lots of open source software. We even open source our research code. So it's a lot of programmers and hobbyists, developer community. But still, there's a lot of people who don't develop at all, but they understand the theory well enough to have coherent conversations about what intelligence is and how it works in the brain. Discourse, which is a Stack Overflow forum software. It's called HTM Forum. We used to call all our tech HTM hierarchical temporal memory. We've really sort of stopped calling it that, but it was still called the forum HTM Forum. We rebranded it.
Okay.
Good evening everyone. I am Vipin Thomas. I'm here to welcome you all for this event. You're going to learn a lot about deep learning and AI in this session today. A little bit background about myself. I'm the chair of the AI certification program at UCSC Extension. This is a new program that we have launched last year, primarily to bring the AI enterprise use cases as a part of the learning pathway, the learning experience here. Because typically a lot of courses as offered in curriculum, deep learning, machine learning, Python, how do you apply them to implement enterprise use cases? So that's the prime focus. And we have a few tracks. People are interested in autonomous vehicles, then they can focus on building projects and capstone projects around that. Folks who are interested in smart manufacturing, then they can pick up use cases on it. So it's very much an enterprise-driven certificate program. So very, very delighted to be here in front of you. But the important thing tonight is the event that we have two great speakers. Let me introduce both of them. Ravi Chityala, he's also an instructor here at UCSC, and he's primarily handling the Python curriculum as well as the deep learning curriculum. So those who haven't taken his courses, he's a very highly sought after instructor in the UCSC. So some of you may know him before. So today one of his main focus areas is to give you a more understanding of the deep learning and where deep learning is headed, so more the principles of the deep learning as concepts itself. Ravi recently joined a new startup. I just came to know a couple of months ago. It's a company called Iron Path, based in Menlo Park as a principal engineer. So he's an engineer by heart. He has a lot of experience in the medical science, especially in medical imaging. So this Iron Path is also in that space of medical imaging. So he's a pioneer and sought after person for applying deep learning techniques in the medical imaging space. And also is a wonderful instructor that we have at the campus. The next speaker we have is Matt Taylor from Numenta. Matt, so he will be handling the second session. Matt would be presenting more about towards the artificial general intelligence. We've heard of AI, but this is AGI. So you'll be curious to know what AGI really means and some of the things that his company is spearheading in terms of creating an open source community around it. And he's actually the open source community manager representing Numenta to socialize the role of AGI and how does this new computing methods or computing architectures are evolving in order to really simulate the way AI works, the intelligence works even in human beings, the biology behind it. So that's another fascinating topic. So he'll be spending another hour with you. And I'm thinking we plan this as some little bit of Q&A right after Ravi's presentation. So he will try to wrap it with a few Q&A before 7:30, and then the rest of the time will be for Matt, and he'll also have time to do some Q&A with you before the session adjourns. So with that, I'm delighted to welcome Ravi.
Thank you. All right. My name is Ravi Chityala. My full name is Ravi Shankar Chityala, but it's mouthful, so Ravi is good enough. I have been teaching at UCSC Extension since January of 2015. That's more than 4 years now. I'm currently teaching two courses. One is Python for Programmers, which is the Advanced Python Programming course, and the other one is Deep Learning. Unfortunately, due to my new job being a little too busy, I won't be teaching the Deep Learning class starting from next term. But what I'm going to talk today should give you enough information that you can actually go and pick up other courses and you will be able to follow what's machine learning and deep learning. Okay, hopefully. My Python for Programming course is going to start on January 24th. So if you're interested, come and join me on January 24th. All right. I've co-authored two books. One of them is, this is the first book I co-authored, which is Image Processing and Acquisition using Python. I've been doing Python for probably around 10 years now. And image processing is my field of my specialization. So kind of combine those two together to write a book. This book is a textbook, a graduate level textbook that teaches you image processing and how does image acquisition work with respect to the medical imaging world. The other book is based on the notes that we give to students at UCSC Extension. Okay. Me and my co-author, we both teach, and we took our notes and we kind of converted that into a book, added more things on top of it, and that's this book, Essential Python. Okay. So this was basically, I would say it's reasonably well done because we actually got feedback from students. Some students will say, oh, this topic is too hard, can you explain to me a better way or something like that. And based on my experience as an engineer, I know what is important and what's not that important, so I kind of make sure that the topics are such that it's useful for everybody. So that's the two books that I've co-authored. So let's get to the main topic. So when it comes to machine learning, there is one fundamental principle I'm going to teach today. Okay? You can take that principle and try to apply it to many other machine learning models. I'll teach it with one simple example of linear regression. And you can actually extend this to logistic regression, SVM, neural networks, CNN, RNN, all follow pretty much the same principle. Okay? Except the scale is different. Linear regression, the equation is simple. Take a neural network, the equation is way more complicated. Okay? So you'll be doing a lot of math, but ultimately the basic principle still is the same, remains the same. I like this way of learning because it kind of helps me not solve one problem, but I actually can solve a class of problems. Many machine learning problems fall into this category. Not all of them, because if you think about problems like decision tree, random forest, they are a different class of problems. Okay? The classification techniques like k-means, k-means table, and all that, they follow a different kind of technique. But it turns out that many other problems come under just this one basic principle. Okay? All the slides will eventually be shared. So if you want to take a picture, go ahead and take a picture, but I'll share them. All right, so we're going to start with something really simple, which is the heat equation. Imagine you have a very thin rod. Okay? Initially, it might not make sense why I'm talking about this, but eventually things will fall in place. So be patient for at least another 10 to 15 minutes. So imagine I have a very thin rod, like this one. It's really long, but imagine it's very thin. So that means the y dimension is pretty much negligible. Only the x dimension matters. Okay? So at x equal to 0, I have a candle which kind of heats up the rod, and that's my candle. Okay? I know I'm not great at art, but I'm assuming you get the picture. So I keep heating one end of the rod, and I leave the other end whatever the room temperature is. And it turns out that this problem has been solved a long time ago. Okay? Like probably like 300, 400 years ago, smart people came and said, oh, this is how the distribution is. The temperature distribution, T, uppercase T, temperature, is d squared T by dx squared equal to 0. Okay? So somebody came to this decision that this is how it's going to be. And because it's a very simple equation, I can sit down and do a simple integral. So I integrate both sides, I end up with dt by dx equal to c1, some constant c1, which I don't know what it is yet. And then I'm going to integrate one more time, I have t equal to c1x plus c2. Okay. Looking at this equation t, with respect to x, you kind of know that it's actually a linear equation. Okay? If you know y equal to mx plus b, you can see the relationship here. Okay? So, which means that if I know at least two temperature on one end of the rod and the other end of the rod, I can actually get the correct answer for C1 and C2, which means I can literally fit a line that goes from that blue line. Okay. So this requires few things. Number one, you need to know the physical equation, which is the differential equation that governs how that rod is going to behave under temperature. Okay? So you need to know the physical equation. If you don't know the physical equation, we can't solve the system. Okay? And traditionally, humans are very inquisitive. We have been doing this for probably thousands of years, not just 300 years ago. We want to understand the world. Okay? We don't want to just pretend like, oh, it happens and I'm just going to leave it as it is. We don't leave it at that. Okay? We ask questions like, why should it be like this? Why shouldn't it be something else? Okay? So these kind of systems, when you have a linear equation, now you can see that you can actually pick any distance, like x for example, somewhere here. And given that the equation of t is equal to some c1x plus c2, given c1 and c2 can be solvable, you can literally predict what the temperature is going to be. Okay? Now, instead of trying to remember lots and lots of temperature, you only have to remember two things. One is c1, the value of c1, and the value of c2. Using just those two things, and knowing the relationship between t and x, you can literally solve for any t, given the value of x. Okay? Now, it's a huge leap of faith for me to tell you that linear neural networks work similarly. Okay? But we'll see how that actually happens. Okay. Now, imagine that you don't have the physical equation. You don't have the differential equation that governs the system. Okay? Now, but you're still expected to solve the system. You're still expected to say, how will the system behave at any arbitrary x? Okay? So, how do we go about doing it? Imagine you take a thermometer, you walk along this rod, and you keep measuring temperature. Okay? At temperature at this position, you measure, and that's this temperature. You measure the temperature at this position, that's this temperature. You keep taking measurements. These measurements won't exactly lie on that line, because you have error in the measurements, maybe some other reason, maybe the reality itself is like there might be some, let's say a slight wind that blows over that rod, and then the temperature might change in that locality. So lots of things that can cause errors. So you will never have a perfect temperature that lies along the line. So you will have some distribution. Okay. Now, given all these points, you will say, oh, I look at it and say, oh, that looks like a line. Okay, that looks like a line, so I'm going to fit a line through this. Okay, you fit a line. Now the question is that line a correct line? Okay, we don't know. We know that that line looks good, at least from what we see visually. But is that a good line? I don't know. Is it even a line, first of all? Is that data such that it's going to be a line? We don't know. If I had the physical equation, I can exactly tell you what the equation is supposed to be. Is it linear, quadratic, sinusoidal? I can tell you what it is supposed to be. But if I don't know the physical equation, I'm going to go by my visual cue that it's supposed to be a line. So I fit a line. Now, I kind of solved the problem. Now, given that line, I can tell you at any point of time, or any point in x, I can tell you what the temperature is supposed to be. Even though all that I did was I measured at, let's say, 10 points. Now I can tell you for thousands of points where the measurements are supposed to be. Okay? Now, the reason this approach actually is important is because many things in the world, we actually don't know what the physical equation is. Okay? For example, if I, later I'm going to show you this example, there is a, maybe I'll just quickly show you this. Oops. This plot. So this is actually real data. In Santa Clara County, Santa Clara City, x-axis is square foot, y-axis is dollar per square foot. Okay. Now, if you notice, if the higher the square foot, the lower the dollar per square foot. Okay. Now, can you tell me what the differential equation is for this system? Maybe somebody is smart enough to know what it is, but I am not that smart, so I really don't know what the differential equation that governs the system. But looking at the data, I see it's a line. Okay? And I say, oh, I'm going to fit a line through it. Okay, it's not too bad. Maybe it's a quadratic, because you see there seems to be like a slight trend coming down like this. Maybe a second order equation may work better. But considering that we are selling houses, especially in Bay Area where anything goes, predicting the price of a house based on whether it's linear or a quadratic is actually not going to make that big a difference. It might both be very similar to each other. Okay? So that's the reality of this world, where there are a lot of things that you can solve knowing the differential equation, but for many, many things, we actually don't know what the differential equation is. Even if you know the differential equation, sometimes it's actually very, very hard to solve the differential equation. You end up making assumptions on what the solution is supposed to be in order to solve it. Okay? That kind of defeats the purpose, because you are making an assumption which might actually violate the reality. Okay? So it's kind of a chicken and egg problem. Can I take the differential equation? Now I know what the solution is supposed to be, but I'm going to make an assumption that means the solution is wrong. Okay? If I just take the data, my solution still could be wrong. Nobody knows which one will work, which one will not work. So you have to mathematically prove it actually works or doesn't work. Okay? And it's kind of hard to even prove mathematically that works or not works. The way we handle it in machine learning is we take the data and break it into multiple parts. We call them training data, we call it validation data, we call it test data. We don't see the test data, we only use the train and the validation, and finally prove the model actually works by using the test data. Okay? So that's the technique we use. It's not mathematically accurate, but it actually works practically very well. Alright, so now you know that given a bunch of points, I'm going to fit a line. Okay, now how do you actually go and fit a line through these points? Okay, and for that there's actually many, many solutions. Right from the time of Newton, people have been coming up with different ways of solving this. The easiest one is you can take a van der Waals matrix, take an inverse, and you have a solution to your C1 and C2, for example. Okay. The other one is Newton first came up with this idea, which was called a closed form solution. It's essentially an algebraic system. You can just solve the algebraic system and you have an answer. Okay. I don't have time to show it here, but I will give you a PDF with my scribbles on it, which solves the closed form solution. Okay. So these are two ways of doing it. But there are actually many other ways of doing it. And there's one clever way that we use in machine learning, which turns out to be very helpful and very, very generalizable. The closed form solution is not generalizable. The van der Waals approach is not scalable because it actually has to take an inverse, and sometimes the inverse doesn't exist. So you can't solve the system. Okay? Whereas the system that we normally use in machine learning and deep learning today is actually a beautiful system, and very simple yet very scalable system. You can apply it to any curve. It doesn't have to be a linear equation. Okay, so let's get back to the linear equation. Here, y equal to wx plus b. We need to find the best curve that goes through these bunch of points. Okay, so that's our ultimate aim. We need to find the line that essentially goes through all these points. Now, we don't know what the curve is, so we decided that we want to fit a line. Okay, that decision we have made. Okay, in machine learning we call that a model. We have a bunch of things and we say we want to fit a curve and we call that a model, so it sounds more fancy. And let's say we decide that I'm going to start with that line. Random. Some random line, some W, some B, some slope and some intercept. I fit that line. Now, is that line good line? Looking at visually, you know it's not good. It's pretty bad. Okay? Because your actual line is supposed to go through this, but the line is actually right here. Okay? So what do you do? What you do is, you have all these x comma temperature. So for example, for this x, this is the actual temperature, the yellow dot. Whereas the predicted temperature is this one. So you say, I got a problem, I got an error. My actual is something, and my predicted is this. I have a difference, that's my error. You take that error, you square it so that you have all positive numbers, and then you sum all these errors. So that means you take the difference between this distance, plus this distance, plus this distance, plus this distance, every one of them squared, you add all of them up, that tells you how badly your line fits that particular data. Okay. Now you say, okay, that's bad, but what can I do next? So I'm going to find a different slope and intercept. And that line might be something like this. Using the information from the past, which is the amount of poorness of my fit, I'm going to figure out a new line. That line might be the second blue line. Okay? The second blue line looks better than the first one, but it's still not good because you see that error on this side is high, error on this side is high, maybe error on these points, not too bad. Okay? So you come up with a new slope and intercept. That might be that. Then you come up with one more. Probably at that point you say, okay, the error doesn't seem too bad. Or you can keep trying. You can keep trying finding new lines. But eventually you can say, okay, I'm going to stop here. Okay. Now, there are multiple ways to generate this bunch of lines. One way is you can randomly start picking lines. You only have two parameters, W and B, slope and intercept. So you can randomly pick a slope, randomly pick another intercept, try. Go and pick another random M and B, try. You can keep repeating it. That's kind of wasteful. Because on a system like this, where there are only two parameters, yeah, it's maybe practical. But if you have millions of parameters, like the way you have neural networks, it's not practical to pick million numbers because it just becomes exponentially big immediately. You pick million numbers, it doesn't work. You pick another set of million numbers, and you keep repeating it for maybe billion times. You don't have the compute for that. Okay? So you can't go by randomly picking stuff. Okay? So you have to come up with a more clever way of doing it. And that way, it turns out it's nothing to do with machine learning, it's to do with optimization. And if you have done engineering courses in mechanical, civil, I don't know about computer science because I'm not from computer science, you would have learned this optimization. Okay? Probably computer science folks do take optimization courses. Where you say that I have a solution, I have something, and I want to go to something better. And from that, I'm going to check whether I'm doing well, and I'm going to go to something better, and I'm going to keep repeating it until I reach something that's really, really good. Okay? And then it involves only 3 steps. Okay? That's the beauty of machine learning and deep learning. There's only 3 steps to it. And some of these steps are just pretty standard. Okay? The first step, you have to define a curve with parameters like W and B. W and B don't have to be 2 numbers. It could be literally like billions and billions of numbers. Okay? In machine learning and deep learning, we call that curve as a model. Okay? And then you have to define measure of poorness of the curve at any time. That means how bad the curve that I just predicted is with reference to the data that I have.
how badly is it doing. Okay. In machine learning and deep learning, we call it as a loss or cost. Different people use different terms. Okay. Then the third step is the optimization. Okay. The optimization step is pretty standard. In the sense, literally, you'll be doing the same thing for most of the machine learning problem. Okay. It's only the first two is different. Okay. Even the first two, the first step, for example, when it comes to linear regression, that's a curve, linear curve. Logistic regression is still a linear curve. SVM, a linear curve. Okay? And neural networks, you get to pick the curve. You get to choose the parameters that you want to use. Okay? The measure of poorness is typically depending on the kind of output you are trying to generate. If you are trying to solve a regression problem, you might have one type of loss function. If you are trying to solve a classification problem, you might have a different loss function. Okay? And within classification problem, there are different classes of classification problem. So you will pick different loss functions depending on the class of classification problem. Okay? So those also are kind of become standardized. Because so many people are working in machine learning and deep learning, pretty much most of these things have become standardized. And the third step is pretty much the same thing you do for any kind of problem. Okay? Which is what I'm going to do next. So previously I talked about loss, and I said it's nothing but you take the actual, you take the predicted, you find the difference between them, you square it, and you sum across all the data points that you have. Okay? Mathematically, you can write it as sum of y hat minus y the whole square, y hat being the predicted, y being the actual. Okay? Because y hat minus y the whole square is positive, the whole square is positive, so this number will all add to something bigger. So that means errors will look bigger. If you just take y hat minus y, that might be small, but once you square it, it looks bigger. Okay? Which is good, because then it tells us that it looks like the error is bigger, then you are forced to actually reduce the error. Okay? Alright, so the equation that we have is y hat equal to wx plus b, and we know the loss function of the cost function is y hat minus y the whole square. So I'm going to start doing some really basic derivatives and calculus. Okay? And I'm also going to use really simple algebraic equation. Like the first two are simple algebraic equations. The first one is linear, second one is quadratic, nothing more complicated than that. That's another beauty of deep learning. No matter how complicated it is just college level algebra, college level derivatives. Okay? And I'm talking about not even college level as in senior level, I'm talking about like probably less than junior level, college. Okay? So I take a partial derivative of L with respect to y hat, and I end up with 2 times y hat times 1. Bear with me for a few minutes, it'll make some sense soon. Then I'm going to find the loss with respect to the weight. I have wx plus b is my equation. So I'm going to find loss with respect to w, which is based on the chain rule of derivatives. It's loss with respect to y hat times y hat with respect to w. Okay? We already know from the previous slide, loss with respect to y hat, and that's the 2 times y hat minus y. And from y hat equal to wx plus b, I know dy hat by dw will be equal to x. Okay? I have dl by dw. Now, there is something called an update equation, which is the last equation, which basically tells you that given a w at any time step I can find what will be the value of w at step I plus 1. Okay? So which means I'm in one line, and I need to find the next iteration's slope and intercept. I'm going to use this equation. Okay? I can apply the same logic to b, because I have two parameters, w and b. So I find w first, then I'm finding b next. The last equation basically tells you how to update b. So that means I have a new slope and I have a new intercept based on my old slope and old intercept. Okay? So I don't have to go randomly searching for the best slope and intercept. I can actually go very systematically from one to the next until I reach the right answer. Okay? And it turns out that many of the engineering problems are solved this way. And machine learning turns out to be one of the engineering problems we solve. Okay. Now, in neural networks, we call this as a backpropagation process. Okay? If you go look up, if you are not familiar with it, go look it up, and you will see this is what they call as a backpropagation process. Typically, we talk about backpropagation only from neural network perspective, but the basic principle is just this. So you have your forward equation, which is your y hat equal to whatever, and your backpropagation is where you go and try to update the parameters of your system, of your curve. Now, in a very generic sense, given you have to find some y, given that it has inputs, x1, x2 all the way up to xn, and it has parameters w1, w2, w3 all the way up to wn, wm, you can solve an equation. Because all that you're doing is, you're given that equation, whatever that equation may be, and you're going to start with some random w1, w2 all the way up to wm, and then you're going to use that update equation to find the new value of w1, w2 all the way up to wm, and you check whether the loss is poor or okay, and if it's not good, you keep repeating until you find an answer that seems satisfactory. Now, we talked about linear regression, that's a regression problem. Now let's talk about classification problem, where you have given two bunches of points, okay, and you have to draw a margin such that, in such a way that you can separate these two groups of points, okay? But this is still a linear regression problem when you look at it, because I'm drawing a line, and I'm saying all the points to one side of the line belongs to one group, all points to the other side of the line belongs to another group. It's different, the only difference is, instead of drawing a line through all the points, I'm actually drawing a line that separates the two groups of points. Okay? But the equation is still exactly the same. The equation is still y hat equal to wx plus b. With one more extra thing, they will add a sigmoid operation to find probabilities. But the equation is still y equal to wx plus b. Okay? But the way we come up with the final outcome is slightly different compared to linear, but still a linear curve. Now, but the reality is not, the world is not linear. Okay, you can make all the assumptions whatever we want, but the world is actually not linear. The world is actually non-linear. Okay, so which means that you can't, in this example, for example, you have two bunches of points and you have to draw a curve. But if you try to draw any linear curve, for example, if I draw a linear curve like this, I'll be misclassifying. Some of the blue points will lie on the red side, and some of the red points might end up lying on the blue side. Okay, so I end up in this classification. Okay, it doesn't matter how I pick. I can pick this one, then this red point is misclassified, and these blue points are also misclassified. So I can pick whatever line I want, a linear line. I will always end up with the misclassification. So the better approach is to actually draw a nonlinear boundary. Okay, nonlinear boundary means I'm actually drawing a nonlinear curve. But no matter what curve I draw, a curve is nothing but a bunch of parameters. I can have w1 x squared plus w2 x plus w3, second order polynomial, for example. Okay, then my job is to find w1, w2, and w3. If I have a third order polynomial, I have 4 parameters. Okay. In neural networks, which is one way of doing nonlinear classification, we combine linear equation like wx plus b with some exponentials, okay, like sigmoid function, or some nonlinearity like ReLU or tanh, in order to produce nonlinearity. Okay? But no matter what you do, it's still a curve with a bunch of parameters. Maybe millions, but still a bunch of parameters. Okay? So as long as you know how to do, how to write the forward equation, that y hat equal to yada yada yada, and know how to do the backward, you actually can solve any equation. Okay? Interestingly, if you use any of the libraries like TensorFlow, for example, you only have to specify the forward equation. The backward equation is actually solved by TensorFlow for you. Okay, you don't have to do it because the backward one is the hardest one, because you have to find all the derivatives and you have to recalculate all these things. But the forward is a lot easier to define. Okay? So TensorFlow expects only for you to define the forward, and the backward will be taken care of by the library itself. Okay? That's another beauty and magic today. 10, 15 years ago, we didn't have those kind of libraries that will take care of all this for you. You have to write all those code. Okay, so coming back to this slide one more time. So this slide, as I said, it's from San City, 1,000 square foot house. Average price is around 1,100 or so. Average price. But if you look at, let's say, a 2,000 square foot house, the average price is like 800 or so. Now, looking at this, we think it's linear. Okay, it actually might be linear because Santa Clara, people, it's expensive. Houses are expensive. They're not cheap. 1,000 square foot house will cost like $1 million in Santa Clara. But still, there's only so much people are willing to pay. Okay, just because you have a 2,000 square foot house doesn't mean it's going to sell for $1,000 a square foot, because people can't afford to pay $2 million for the house. They're okay to pay maybe a 1.5 million, maybe 1.6 million. That means $800 a square foot. But expecting people to pay $2 million, which is $1,000 a square foot, is kind of impractical in Santa Clara. So in that sense, it sounds very linear. The relationship sounds very linear. Okay? But notice that there's also a huge spread. There's a huge spread, for example, here. So which means there might be other confounding factors that we actually are not familiar with. Okay? Or we are not accounting for that in this particular graph. Okay? So which means when I fit a line through this, I'm making huge amount of assumptions. Okay? That I'm ignoring all the confounding factors that I'm not familiar with, that I might not even know they exist. Okay? For example, this, I don't know whether it's in a specific year, but let's say it's over a 3-year period. Okay? Over a 3-year period, especially in Bay Area, prices have changed. Okay? Let's say, for example, if this was from, let's say, 2009 to 2012, for example. Okay? In 2009, house prices were lower and they were just coming up in 2012. Okay? So which means that houses at the bottom here, maybe were houses that were sold in 2009, and houses here were sold in 2012. Okay? So there are a lot of interesting detail that's actually missing from this graph, but it kind of gives us some sense of us, some sense for us. So what I'm trying to say is that just because we see a linear relationship, it doesn't mean it's actually linear. Okay? So last 2 slides. The proof for linear equation that I showed earlier can be extended to any curve, including nonlinear curves such as neural networks. The model we fit only works for that range. For example, if I take this particular data and I fit a linear equation from 1000 to 1500, okay, claiming that equation will actually work for 2500 is kind of dubious, because there's no way you can prove it. Okay, maybe by testing it, yeah, you can prove it, but that's still empirical. Okay, so which means that if you are trying to fit a curve or do any machine learning and deep learning, make sure that you are basically doing interpolation, not extrapolation. Okay, for example, if I give a deep learning model where I train cat versus dog, I give all kinds of cat images, and I never give it dog images, or I give very little dog images, and later I expect it to spit out dog images perfectly, prediction of dog images perfectly. It's not going to work, because it doesn't see the data. That means the range of data that I provided is not the kind of range it's actually expecting. Since these models are based on data, which means poor quality data means poor quality fit. Okay. For example, again, I'm not a climate scientist or anything, but let's take a scenario of predicting temperature, outdoor temperature. Okay. And I am using information like how many people live in a neighborhood as a measure of temperature. Okay. But that's not exactly a good measure, because if you look at San Francisco City and New York City, they both have probably equally crowded. Okay, maybe New York City is more crowded, but they are likely to be equally crowded. But the temperature is completely different. Here it's 60 and there it's like minus 20. Okay, so the number of people living in a neighborhood has no correlation with temperature. If you plot it, probably you will start seeing a pattern. And just because a pattern exists doesn't necessarily mean it's actually the right thing to do. Okay, so which means you need to be careful what kind of data you feed to a system. Because the system can always come back and say, oh yeah, take it. Here's the model for you. Okay? Because from the system perspective, from the computer system perspective, it's just fitting a curve. So it doesn't know whether it's fitting the right curve or not. It's up to us to judge whether we are actually providing the right kind of data. Okay? Fitting complex nonlinear model needs more data than simpler models. It's kind of obvious, because if you have a simpler model like a linear equation, you only have 2 parameters. How much data do you need to find 2 parameters? Not much. But if you have millions of parameters, obviously you need more data. Otherwise, it will be like you're guessing what the parameters are at that point if you have very few data. By chance, maybe the guess might be good, maybe it's not good. Nobody knows. Okay. So if you know the differential equation of a given problem, then you know the curve exactly. Then you can solve the problem exactly, right? But if you don't know the differential equation, which is true for most of the cases, that most of the problems you're trying to solve, which means that you start by assuming a certain curve. You say, I am going to assume linear and see where it goes. Okay? And then you do your testing. And then you check whether the testing results are good. If the testing results are not good, you go back and say, okay, I'm going to try a different model. Okay, linear didn't work, let me try quadratic. Okay, quadratic didn't work. Okay, let me try a third order polynomial. Oh, that didn't work, let me try neural network. And you keep repeating it. Okay? That's basically what the comic is telling. It's basically a big linear algebra system where you keep throwing in data. If the answer is not good, you keep stirring it until you get the right answer. Okay? It's kind of like beating a dead horse, if I were to say it very jokingly. You keep beating it until it gives you the right answer. Okay? And the beating is done by you, but the computer is the one that's taking the beating. Okay? Jokes aside, that's the reality because we don't know the physical equation of the system. If you know it, yeah, then you can make some, oh, I know exactly what it's supposed to be, and you can go exactly to that equation instead of trying all kinds of things. Okay. Interestingly, we didn't start like this when it comes to neural networks or CNN. We didn't start like this. They all started from a different direction, which was we wanted to understand, we have a biological system, and we wanted to see whether we can model it mathematically. Okay? But it turns out, no matter what direction you start from, you ended up here. Okay? So this is, in my view, is like a more unified way of looking at it. A curve fitting is a unified way of looking at most of these problems. Not all problems, but most of these problems. But they all started for different reasons. Okay? Which is how history always is. History is never linear. History always goes in all directions, and then eventually you all end up at the same place. So yeah, so that's my talk. If you have any question, feel free to ask. Yeah.
You used error squared as the loss measure. Is that typical or just simple for the example?
So there's so many different error functions. Okay.
I feel better.
Exactly. Yeah. Good. So that's one line answer. But the bottom line is you pick an error function that depends on the problem you're trying to solve. If it's a classification problem, you have a set of loss functions. If you have a regression problem, you might have a different set of loss functions. Today the problems have gotten more and more complex. So we sometimes combine loss functions. We might have 2 or 3 loss functions. We combine all of them together to produce one loss value. Okay. But ultimately, the bottom line is there are 3 steps. Determine what the model is supposed to be. Determine what the loss function is supposed to be. Start optimizing. Keep repeat until you get the answer. Another question? Yeah.
I was thinking about error functions too, like that one where you have a group of x's on one side and a group of circles on the other. Oh, it was that. No,
Oh, sorry.
not that error function. Over your
Oh,
sheet.
yes.
Yeah. And I was thinking the error function there would be something like minus all the minuses on one side, all the pluses on the other side. The summation should be. There aren't any. The things on the right, you ever get plus, and the things on the left, the distance never gets minus.
Okay.
Something like that. So
There are different ways of doing it.
Classical square error function.
No, you cannot use the classical squared error function here because there is no concept of the actual value.
Right.
So different classification problem are different loss function. For example, logistic regression has something called logistic loss, okay, which is basically you try to find the probability of these 2 groups of points, okay, and then you have an equation where you plug it in and it'll tell you what the loss function is. It's kind of hard to say, even if I say it, it kind of won't click in people's head. SVM has another different loss function. It's called a hinge loss, okay, which uses the fact that which labels one side as -1, the other side as +1, and uses that to determine what the loss is. Okay, and when it comes to neural networks and all that, we generally tend to classify multiple classes. We create multiple classes in the output. So in that case, we have something called a cross entropy loss. Okay, that's a different kind of loss function. So this basically it's kind of hard to explain right now, but if you go look up logistic loss, hinge loss, cross entropy loss, you'll get an answer. Okay. Those are 3 common ones, but there are also other ones as well. Yeah.
Are there tools available that sort of can identify in the neural network when it's overfitting and or when you have insufficient data to generalize properly?
Okay. So first I want to your question, let me answer your question, but before that I need to say something else. One of the things you would have, whatever I discussed, one thing you would have realized is if your data is garbage, model you get is garbage. Okay. So that means you have to spend a lot of time making sure your data is good. Okay. It's reasonable. I'm not saying it has to be perfect, but it has to be reasonable. Okay. So it turns out 60-70% of the time that data scientists and deep learning engineers spend is actually on making sure collecting data, preparing data, and curating it in such a way that it can actually fit to a deep learning model. Okay. The reason we don't spend as much time on deep learning is because most of these libraries are really simple to use. In fact, most of them, you actually pick a model that already exists. It means you pick a curve that already exists. You might say, I'm going to use ResNet. ResNet is one kind of architecture in CNN, and that is a specific curve, and you just pick it and use it. Okay. Considering that scenario, the amount of work you do is actually mostly on the data preparation part. The architecture is generally something that you pick with whatever is available, whatever is used a lot, or very popular in the area. Okay. But that doesn't mean you should not change the architecture, but very less likely you will actually be changing it. Very likely you will actually be using existing architecture. Sorry, your question?
Are there tools available to identify overfitting and
Okay. So,
insufficient data?
so here I want to point out something called AutoML. Okay, AutoML. Because if you think about the process, you start by defining a model, you define a loss function, and then you optimize. Okay. Now imagine you do an experiment and you create 5 different models, and for the same loss function, 5 different models, and you run model 1, model 2, model 3, model 4, model 5, and you notice that model 2 and 4 are doing okay. Okay, the other 3s are cut. Okay. So now, this seems like something pretty straightforward that a computer can actually do. Why should a human being get involved in all these things? So that's why most of these companies have created something called AutoML. What it does is, you specify n number of curves. You say, I want to fit 5 different models or 10 different models, and then it will take certain number of hyperparameters for all those models, and it will start running all those models in parallel. Okay? If some of those models are performing very poorly, it just stops. It could be overfitting, or its loss function is not decreasing properly, or some such problem, it just stops it. The models that are performing well, it keeps moving forward. At a later time, if some of those models tend to degrade, it stops those models, and only the ones that survive is actually given as a final outcome. Okay. So essentially, we don't have to do it anymore. Most of these things have been packaged for us. Okay. If you use many of the cloud services, they have an AutoML things for us. Yeah, let me take that.
What's wrong with overfitting? So I was just wondering, this might be naive, but if you have the Santa Clara housing prices, you have all those data points, and you connect each data point with a small line, and then you build some sort of a composite function, so that isn't that a much more accurate function?
You mean like a piecewise linear? Yeah, you can. But the thing to understand is that mathematically it's all fine, but in the real world, how does it actually work? Okay. Let's say, for example, you're going to determine who gets loan and who doesn't get loan. Okay. Now, if your model is not good, it might end up rejecting people who should be getting loan. Okay, which means we might be marginalizing a certain group of people. Okay, so it's not mathematically, it's not possible fitting any curve from that matter. It's what is the outcome of this for the real world, because we're going to make decisions based on this. So if you remember the heat equation example, I only have temperature from 10 different points. Now I can say, give me any x, I can tell you what the temperature is supposed to be. Okay. Now, if you apply the same logic to giving loan, give me a demographics of 1,000 people, and I can tell you who should get loan, who should not get loan. Okay. You give me one more person, 1,001th person, I can tell you whether that person should get loan or not. Okay. If my curve is biased or has some problem, then the 1,001th person may get loan or may not get loan for right or wrong reason. We don't know. So it's more about the reality of the outcome rather than the mathematical part of fitting a curve. Because fitting a curve, yeah, you can fit most of the curves. In fact, you can fit a nice exponential curve just in that region. It kind of drops. So if you think about when an exponential curve drops, the point at which it reaches close to the bottom, that point looks very much like the Santa Clara County housing price. Okay. Yeah, I can use that to fit, but would it work? Yeah, it might work. And housing price is not that big a deal because people are overbidding in Bay Area. Okay. So if you say it's going to sell for $1 million and people end up paying 1.1 million, well, okay, it's not a big deal. It's not a big consequence. It's a consequence of the person who paid for it, but generally speaking, it's not considered a big consequence. But if somebody is supposed to get a loan and they didn't get a loan, It could affect next 3 generations of people in their family, for all that we know. Okay. So it's a reality, that's all. Yeah.
Just to continue the previous question, is there a relation between the number of the training data and parameters, let's say neural network?
There is no simple way
But
of saying
in
it.
order to avoid this overfitting.
There is no simple way of saying it. You just have to try it because
But
your
in
curve is so
in your practice, like how much difference?
it's kind of hard to say.
Like you said, like the 2 parameters, 10 data was sufficient for you in this case?
Literally, if you have 2 parameters, two exact measurements will be more than sufficient. Okay, but the reality is we don't have exact measurements. So that's why we need more data, more than 2 points.
And like I saw some papers, for example, saying that neural network was 10 layers, and each layer was 1,000 of units in it, and they're only using like thousands of training data. I was like, wasn't even like, is it like too much overfitting, or if they're using visualization, it may just work well?
Yeah, as I said, it's kind of hard to say. You have to try it. You have to try it to see whether it's overfitting or underfitting.
But
So-
still, like, for, let's say you say there's million parameters, right? For those million parameters, what kind of data sets should be?
So million parameter doesn't mean you need billion data, okay? Because your model, depending on the data, maybe the model is complex or simple. It's kind of hard to say. Let's say if you take the Santa housing price itself, okay? If you fit a neural network through this, the model may not be that complicated, okay? You can fit a nonlinear curve using neural network, and the model might not be complicated. But if you take the same situation of, I'm going to predict dog versus cat, or human versus no human. Now you're giving millions and millions of pixels, or 1,000 image, for example, that's a million pixel. You give million pixel as an input, and you ask it to learn. It's kind of hard to say what the accurate answer is. You'll have to try it. Okay. I listened to podcasts on machine learning and deep learning, and in one of the podcasts, a listener was asking this question: if I pick a model, okay, I pick the loss function, and I keep iterating through it. I try something, it doesn't work. I try something else, it doesn't work, and I keep repeating it. Then what is machine actually learning? Okay. When you really think about it, it's actually I'm the one who's learning. I'm learning the fact that this curve doesn't work, that curve doesn't work, that curve doesn't work. This works. Okay. We are essentially using computer as a means to compute. Okay. But the person who's actually learning is us. With AutoML, what you're doing is you are trying to let the machine decide some aspect of it, but still, you are the one who initially made the decision of using certain number of models. Okay, so you are still making decisions. So it's not truly machine learning, but it doesn't mean it's simple. Or it doesn't mean it's not useful. It's actually very useful because even this simple idea, imagine the kind of problem it's solving. Imagine the number of people who are being employed, probably billions and billions of money being made using just this one simple system. That itself is beauty. Forget everything else, just that one thing alone is beauty. Yeah.
Could you go back to the slide with housing prices?
No, sir.
So a couple of questions. I look at this and I say, with only giving us 2 data points, right?
Mm-hmm.
I don't think you can solve this to a sufficient low error rate for the exact reasons you mentioned, that we're leaving so much important data out, right?
Mm-hmm.
Like you said, when was the home sold? What is the zip code of the home? 3 bath or 1
Exactly,
bath, right?
exactly, yeah.
So if you tried to solve this in this methodology, would you, I'm assuming the indication would be when you use the formula to then compare it with additional data, that your error would continue to be high if you only had the 2 parameters?
The way I see this particular data set is that when you talk to a realtor and say, I want to buy a house, they will go look up all the houses that are sold in the, let's say, the last 1 year and say, oh, this house near this particular property was sold for this price, or your house is going to be sold for this price. Okay. So a human is sitting down and curating all this information and trying to predict the price. So here we are letting the machine make the decision for us. Okay. So now the question is the human doing the right thing? Nobody knows, because sometimes the human says, oh, your house will get sold for 1.1. Okay. But then somebody comes in and says, I need this house urgently. I'm paying another 100K more. Okay. You might be lucky in that sense. Or somebody might be unlucky. They might put it for 1.1 million and the market is tanks. And then suddenly now they're only getting 900K. And let's say they have to get it over their hand. they are willing to take 900K for the house. Okay, so this is all just to give us an idea of where we might land, but I wouldn't go by saying that that's exactly where it's not get sold, because the houses at the bottom probably they are not good looking. The houses at the top probably are good looking, but the question is, what does that even mean? Okay, good looking is a very subjective thing. What I think is good looking is different from what other people think is good looking. Some people might come into market thinking they want a brand new house. Everything should look shiny. Some people might say, I want a house that is decent enough that I can live in while I fix the house. Okay, so different people have different requirements. So it's kind of hard to say. We can't just rely on this alone. That's what I'm trying to say. Okay, but it's still a good starting point. Good starting point to know where we will be landing.
Well, and I guess to build on that, I look at this and I say, okay, I could see building an equation with maybe 30 parameters. You know, if I really wanted to see how good, how precise, how small an error I could take, what would it take? And it would take significant more than just.
Exactly.
Yeah.
Significant, not just computation. Computation is probably the easiest part, collecting the data.
Right.
Okay.
So
and then understanding the data. If I have one more axis, which says the, I don't want to use the term beauty, but it's more like likability of the house. Okay. There's another axis I call likability. What is likability? You might say something is likable, and I might say that same thing is not likable. Okay. So which means I can't even quantify likability. So which means that whole axis is actually dubious. Okay, it's not a quantifiable thing. Whereas square foot and dollar per square foot, that's a very quantifiable thing. You can go county records and it will tell you exactly what price the house was sold. And you know how much square foot that house had, so you can actually tell exactly what the dollar per square foot for that house was. So yeah, it's hard. It's a hard problem. Machine learning is beautiful, but it's collecting the data is actually super hard. Yeah.
So maybe probably a lot of people know that I didn't realize that this was such a technical talk, but it's very interesting anyway. But what is a neural network? What do you mean by that? Could you explain it a little bit?
Okay, so in the case, how do I say it? It's a nonlinear curve. Let's take it simple. Okay, it's not polynomial. It's actually it has exponential. It has some other nonlinearity if you add them, and also some linearity. Okay, but it's an exponential. It's a nonlinear curve. That's
so it's data that falls into a nonlinear curve, or it's the curve
you
itself?
you decide that you're going to use a nonlinear curve, and you ask the data to see if you can fit the nonlinear curve.
Oh.
You can find the parameters for that nonlinear curve.
Okay.
Yeah. Yeah.
Can you talk a little bit about ensemble learning, where you basically take various models and then I've heard those can actually be better predictors than an individual model, and how that gets used in real life.
Okay, so if let's say I pick 20 different models, I try all 20 of them, and let's say only 5 of them pass. Okay, 5 of them are giving good results. Then I can say, which one do I pick? Oh, I have 5 of them, all look pretty good. Okay, so one approach you can take is, when it comes to time for prediction, you can say I'm going to give my input to all the 5 of them, and ask all of them to predict, and I can take the average of all of them, if it's a regression problem, for example. Or I can take all the prediction for the classification problem. I can take all the prediction and say which one is the most likely prediction. If all of them predicted dog, then I'm very confident it's a dog. If 4 of them predicted dog and 1 of them predicted cat, I still feel confident it's actually a dog. Okay, so you could use that approach also. But in ensemble, you can take all the models together, whichever seems to be doing okay, and then you can take some kind of a composite of all those outputs and say that's my prediction. You have a question? Let's keep it the last question.
Yeah. This is not, I'm lost in the math.
Don't worry about the math, but just understand those 3 principles, decide a curve, decide a loss function.
When I took the courses a long time ago, I'm still lost. What strikes me in the 1,000 to 1,500, just visually, I see a clump of data.
Mm-hmm.
And I'm just wondering, in this scatter, as a human being, I look at, gee, if I threw out that clump of data, and then I try to fit curves, does the computer do that automatically, or is it just absorbed into the?
So you can remove certain number of points and fit. Okay, the curve might be different.
But
you can still fit a line.
When you do the formulas, if you keep the clump in, you're going to affect the general
Exactly.
curve. So does the computer identify that clump and say pull it out and see what it looks?
On what basis? On what basis can it know which clump to remove? until you tell it what to remove. It cannot remove stuff. There's a technique called ransack. I don't know the full form of it, but the idea is that if, let's say, I'm supposed to fit a line, okay, and there are some unnecessary outliers really far away, okay, I want to remove those outliers before I fit, okay. That is generally for getting good fit, okay. Whereas here, those clumps of points, they're still lying along that line. They're not exactly, you can't say for sure you should remove them, okay. Maybe you have reasons to say they should be removed, but it's not very obvious why you should remove them, okay. But if you want to remove them, you need to tell it how to remove it, okay, because by itself it doesn't know what to remove. You're saying use all these points, then on what basis is it supposed to remove things? So, yeah. Oh, I think I don't want to take too much of time. Matt has a very interesting knowledge graph, but I'll be here after 8:30. We can talk. Yeah.
The data that's here reflects that the average size of a house in Santa Clara is a certain set point, which is around 1,500-ish square feet. That's
Exactly.
partly what you're seeing in that cluster.
Exactly. Somewhere between 1,000 to 2,000 is the Santa Clara houses, because the lot size in Santa Clara is not that big. Okay, I lived in Minnesota where the lot size is like they measured in acres. Here it's measured in square foot, okay? Maybe thousands of square foot. So it's kind of a weird feeling to see that and this. But imagine you have a 5,000 square foot lot, you can only build so much. You can't build a 10,000 square foot house or 5,000 square foot lot. Okay, cool. Thank you so much.
Should I go right in, or do we need to take a 5-minute break? Is everybody okay?
Right in.
Go right in. I'm going to go right in. Wait. All right. Testing. Works. So I don't have any math. Okay. But so the good news is, if you struggle with the math, it's okay. You can still understand how intelligence works without understanding how to navigate gradient descent through backpropagation through a neural network. So, again, I should probably note that I'm live streaming this. Thanks to the viewers who's watching. There's been about 40 people watching this as we've been presenting, so thank you all for joining. Whenever I have like a group of people in front of me, I always like to ask this question. How many of you think human beings are intelligent? Raise your hand if you think human beings are intelligent. Please, I mean, everybody should have their hand up. And watch the hands go down. How many think chimpanzees are intelligent? How many people think dogs? Let's say, in general, dogs. Who says dogs have intelligence? Okay, just look around. Most of the people who say dogs. Cats? More hands just went up for cat. Okay, rats and mice, let's say, rodents. Most hands are still up. Okay, let's talk about a lizard. Would you say a lizard is intelligent? An iguana or something like that?
If you compare, let's say, with stone,
The point of this exercise is that everyone has different definitions of intelligence. Let's keep going. Grasshopper. Who thinks a grasshopper is intelligent? How about an ant colony? Tricky, right? Who believes that an amoeba is intelligent? There's still some hands up. Who believes that plants are intelligent? There more people think plants than amoebas. That's amazing. Okay, so there's this big, broad definition of intelligence that everybody's going to tell you something different. So, I'm going to define intelligence in basically by trying to explain how the brain exhibits what anyone would call intelligent behavior. This is all biological. I am going to do a quick review of deep learning because we just sort of seen deep learning. That was a very simple. I mean, the math is hard, right? But that was the simplest way to understand all of the math, is what he just gave you. And it's super hard to understand that. I went through this process a couple of years ago because I thought, maybe I'm missing something. I thought I understood, a lot of things about the brain. Maybe there is something in deep learning networks that I'm missing that's going to lead to AGI. And so I took the courses, I studied it, and I don't think so. So how close are we to AGI? From the deep learning perspective, I'm going to point out a few things that just really sort of make it poignant how deep learning fails. And I'm not doing this to be mean, I'm just doing this to be realistic. So this is an adversarial attack. All deep learning networks are susceptible to some type of adversarial attack. In the case of an image recognition network, there's some combination of input to the system that will short circuit it. And if attackers can find some combination of this input, they have the ability to short circuit the system. And the tricky thing is, look at the randomness of this thing, right? That means there's a lot of random combinations that could potentially short circuit the system if something weird comes up that it's never seen before, no combination of anything. So it just kind of shows you that there are inherent flaws in the landscape of deep learning because it's really built on mathematics. And a lot of the models that get created can be referred to as brittle in some ways, in that if you show it something outside of the set of things it's ever seen before, it will fail catastrophically, right? Here's another example of adversarial noise. You can apply noise to images that humans can't even see that will cause classification networks to fail. And this isn't just for images, this is for all types of deep learning networks, the ones that process voice input, because they're all essentially doing the same mechanism that Ravi just told you, and that is what's being attacked, that mechanism. One more, probably the most dangerous one, is a misclassification of a stop sign as a 45-mile-per-hour sign. Reinforcement, and this really drives home, if you know what reinforcement learning is, it's sort of the current technology that allows you to get motion into the system, some form of movement or agency into a system. And there's this field of deep learning called deep reinforcement learning. I'll talk a little bit about that later. These systems are extremely susceptible to adversarial attacks because every component that builds up a representation using these gradient descent methods are a possible way that it can be attacked. And if you're moving through space and time as an agent, everything you're seeing is a surface area for attack. It's just, our brains don't work like this. You can short circuit human brains for sure, but they're certainly not as easily fooled as these systems. I probably should have said, I work for Numenta. My name's Matt Taylor. I just sort of went right into this and started talking about intelligence. I am the community manager for a company in Silicon Valley called Numenta. My company was founded to try and understand how intelligence works in the brain and build systems built upon those principles. So we've been around since 2005, and we've learned a lot about the brain, and that's what I'm going to talk to you about, what we've learned about the brain. One more example of deep learning. Again, did you guys see AlphaStar? So this is insane. Like, the things you can do with deep learning are insane. And you're going to keep seeing things like this happen. So, was it DeepMind? DeepMind decided to create an AI that could play StarCraft 2. And so they did, and it's basically beat every human StarCraft 2 player on the planet. Like, it is really good. So they've got it out there, like, on the servers, it's out there. You can go play it. Like, you can go play this AI and lose yourself if you want to feel awful about humanity. But the thing is about this agent, all it can do is play StarCraft 2. It can't really do anything else. That knowledge of, if you want to call it knowledge, of the StarCraft 2 universe doesn't transfer anywhere. And the amount of training that this thing took, I'll say to you this, I actually saw this in a presentation from a DeepMind engineer that worked on the project. The agent that ended up beating all those humans, 600,000 years of like in-game playing. If you were to make the computer play it like in human time, 600,000 years. So you imagine how bad it is for the first several 100,000 years, right? We humans don't learn that way. It's not the way that we learn. And even these things are also susceptible to adversarial attacks. If you knew how this system was architectured, and there's a whole paper about it online, you could figure out how to do it. Okay, so I'm telling you that deep learning is not going to lead to AGI. Why not, right? Okay, there's two big things. The main thing is that the perceptron, the point neuron at the core of deep learning, is a little bit too simple. So all of these deep learning networks that Ravi talked about, are layers and layers and layers, and they all have units, and each unit is inspired by a neuron. Of course, these things were built back in the 60s and 70s. You know, these ideas were emerged way back then. And it's only been until now when we've had the massive amount of compute power to actually do things with them. So this perceptron neuron is vastly too simple. It's basically one unit is a sum of the weights from the previous layer, and you run an activation function over it. Actual pyramidal neurons in your brain are more complicated than that, probably vastly so. We at least know that a neuron in the brain doesn't work like that at all. It reacts differently when it gets synaptic input close to the cell body than it does when it gets synaptic input far away from the cell body, than it does when it gets synaptic input from the apical tuft, which is feedback. So there's a lot more going on in a pyramidal neuron. We have a model for this neuron that we've used since 2010, and what it enables is a network to learn with a context. In our case, learn with a temporal context, which means the state of the network learns by looking at the state of itself over time. That's what this context is. This is the input. This is like the world coming at the neuron, and this is contextual information, and this can be vast. Like this network right here is distal segments of thousands of hundreds of synapses. So this thing acts like a coincidence detector. So when it sees all that, if it sees input on these far away dendritic segments, it can inform the cell that it's about to fire next. That's what this context is doing. So pyramidal neurons actually can go into a predictive state where their voltage increase is not enough to fire an active a spike, but enough that it will beat all of its neighbors from firing. And this is, again, we have lots of theory about this at my company. We think this is how sequences are learned in the brain, which is really important. The second thing that's missing, aside from the neuron model, you have a question?
Yes, if you return to previous slide, basically what it shows, but you collect information, but you do not transfer it to, let's say, next neuron.
Oh, absolutely. Yes, we do. All the neurons are interconnected together.
But in your slide, it's no output.
This is the output, is the activation of the cell body. There's an axon that comes out of the cell and goes to other places in cortex or of the brain. Yeah, the action potential gets transmitted over the axon to other cells that are listening on their dendritic segments, and that can go all over the place, depending on where it is in the brain, what type of cell it is, etc. Yeah. Okay, so the other thing that we're missing from these deep learning models, and this may seem strange at first, but it's the idea of movement and time as a core representation of reality. So can anyone think of anything that is intelligent that does not move through space?
For a time.
What?
Just time. If you take Einstein model, time doesn't have space.
Is that intelligence?
The Borg.
The Borg. Well, it moves, right? They move. Everything moves. Everything that has intelligence moves. Let me give this to you another way. And I say time because the brain sees movement in the same way that it sees time. Sure.
A computer, a theoretically intelligent computer, wouldn't be moving very fast.
Well, we don't have theoretically intelligent computers. Let's think about movement in a different way. It doesn't have to be physical movement. Right, so all you need to be able to do is take an action that changes the perspective of your sensor in your environment. That's movement. So now we need to talk about how brains represent space and time. I'm telling you how important space and time are. So let's go way back. I know we want to nail down like human level intelligence, but to get to this core mechanism, it's like so important that we need to go way back to like the beginning of life, before brains, where we really just have these sort of, these agents that just have neurons that are like photoreceptive or chemical receptive, and other neurons that do some motor control. Think about very simple organisms that basically are already locomoting through whatever primordial ooze is they're existing in, right? Locomotion comes before intelligence. Locomotion exists before we have neurons that have to take action, because that's what they evolved to do. You have to have some form of locomotion. So in the very simplest ideas of how this evolved, we have some simple organism, some type of external stimulus that indicates something good that I want to go to or something bad that I want to get away from. That chemical trail, or that whatever that is, this thing learns that when it sees that, it activates this motion and it gets the hell out of Dodge. Or it sees that and it activates this motion and it goes and eats its dinner. This is how core this idea of movement and space is. Intelligence, the very emergence of intelligence as a survival strategy already involves space, an object, and a movement associated with it. So these are like the core primitive ideas, I think, of how to define what intelligence is, at least in biological systems. We also know of the existence of location-based cells in the brain. In 2014, the Nobel Prize was given for this discovery of something called grid cells. There's different types of these cells that we found in cortex, hippocampus and entorhinal cortex. And they respond to where an organism is in a room, and they seem to map out space. They do map out space. Like we've done, when people realized this, they were like, holy shit. Right? And so they did a bunch more experiments. And this is a real thing. Like you have neurons in your brain that fire in a certain pattern as you walk across the room and keeps track of where you are in your environment. And they do the same thing whether you're in this room or another room or another room. They are generic space mapping neurons. They're things that respond to just space and where you are in it. So we think this is a core mechanism to intelligence. I'm telling you how important space is and time is to the brain. We see there's a way the brain's representing space. And the way that we see it doing it, it can do it one-dimensionally, it can do it two-dimensionally, three-dimensionally, n-dimensionally. Like this mechanism allows the brain to represent n-dimensional space. And that kind of blows your mind if you think about it. Okay. Okay, I'm going to show you some brain diagrams now. We don't have to understand all this, but so this is a very old relative of ours, an ancestral vertebrate. This is before the explosion of the mammalian neocortex. Okay, so this is, we have cortex up here, but it's not necessarily the neocortex because it hasn't exploded. But even in this simple organism, and this schematic sort of shows you the size of the different brain regions and how they're connected, but it's not actually like anatomically correct, but it's more of a schematic view. But these areas that I've circled up here, that's where we think, well, that's where in today's mice, we've seen those location cells. So if you were to trace mice all the way back, the area of the brain that we see that is right there. I bet that even way back then, this stuff was happening back there. I bet this originated when we were all just little tadpoles going through the primordial soup. We started mapping space then. What we have now is this really sophisticated system of mapping space. Because what happens over 500 million years, watch this green dorsal pallium, it expands to take up 70% of your brain. So nature doesn't do this unless something really good is happening in that substrate. This whole green area up there is almost entirely homogeneous. I mean, like, if you poke a pin in this part of your brain, and this part, and this part, and this part, and this part, you'd have to have a pretty good neuroscientist to be able to tell you which part of the brain they just probed. Like, if they could look at the structure of it. Your neocortex, this green part that's doing all these different things, is essentially running the same cortical function all throughout the whole thing. That seems important. And I think that this explosion, this was so useful. Let me explain how useful this is. What the brain basically did here is said, I've developed this mechanism to map my agent in space, where I am in space, But as the brain expanded, and as mammals in particular started evolving dexterous fingers and vocal cords that could really evoke different types of sounds, these space mapping cells in the circuits they were involved in evolved to start representing all objects that we interact with. So now it's not just where am I in the room that I'm in, it's where is my finger on the object that I'm moving across. So this core mechanism that we find working in mice and rats in the entorhinal cortex and hippocampus, we believe has been hijacked in some way by evolution way back in the timeline and evolved into what we think is happening in neocortex right now. And that's where all of our detailed memory about every object that we've ever interacted with is stored. This cortical column, this is a term, an old neuroscience term. This unit that I keep talking about that is replicated throughout the neocortex is called a cortical column. What we do at my company, since I've worked there, is try to figure out how this works. Because the cortical column is complicated, it's 6 to 10 layers, depending on who you talk to. There's a bunch of different cell types in there, and they're all piped into other layers in different areas of the cortex, in different places of the brain, in different layers. It goes through the thalamus. It's complicated. This is a messy system. A little pitch for my company. I live stream all of our research meetings. This is one of the things we do. We research the neuroscience. Like, we just had a research meeting this morning. We were talking about grid cell firing, a hybrid mechanism of grid cell firing using continuous tractor networks or oscillatory interference dynamics. So that's the sort of research meetings that we have, and we do this pretty much every week. If you're interested in this stuff and you want to learn more, my company is very transparent about everything that we do. So, quick pitch. So this 1,000 brains idea, that's what we like to call it. That's our marketing pitch, the 1,000 brains idea, right? That every cortical column in your cortex is essentially doing the same thing, that we can try and simplify the basic function of intelligence down to this one sensory motor loop. And the sensory motor part is important, and that's coming. All throughout our brain, all these different parts of the cortex are functionally different. They're doing different things. There's language areas and speech generation areas, auditory areas. But we think if we can figure out this core algorithm, it will inform us on all of the brain. The hierarchy of the brain. You didn't really talk much about hierarchy in deep learning networks, but it's very important in deep learning networks to learn structures of things to have a hierarchy. And that's inspired directly by neocortical hierarchy in neuroscience as well. There is a hierarchy in your brain, and this is what it looks like. It's really messy, and it's really confusing, and neuroscientists have been trying to figure out how it works for like decades and decades. It's not deep, it's wide, and it's really scattered, right? There's connections going all over the place. I'll talk more about that in a minute. And we think that at every level of the hierarchy, the same essential function is going on. So I'm going to do a hierarchy example. This is what people think the hierarchy does in the brain. Okay, but this is not how hierarchy works. This is like the deep learning model of hierarchy that you might have learned in textbooks and stuff. I'm going to show you this, and I'm going to show you how it really works in the brain. So in a deep learning hierarchy, when you're sending input into like the first layer, you only send input to the first layer. There's more complicated models where you get level skipping and resonance and stuff that try and do tricky things. But for the most part, you send input into the bottom layer. The bottom layer, in the case of image classification, is just an example. The bottom layer will do basic feature extraction. We'll try to identify low-level features, edges and points and dots and things like that. And then it passes its new representation to the layer above it. And we ascend the hierarchy, right? As you go up the hierarchy, the theory is that the layer above will take those components and compose them in a logical way. In the horse idea, taking some of these edges and turning them into feet and legs and torso or whatever. And then as you get to the top, that's where ignore that. This is from a video, I make videos. At the top, you actually get the object that's being classified. So this is how all of the machine learning textbooks show hierarchy, but it's actually not even this clean. If you look into real neural networks, you can't like look at one that has nose faces and see noses at some point. That everything gets mangled and mashed together. So there's no logical composition of features like a human would do, right? But okay, so the brain's different. This is a bit of a toy example, but everything I'm going to say here is, I think, factually true. In the brain, I'm going to use the visual cortex as an example. Input flows feed forward into multiple areas of the hierarchy. Okay, it doesn't just go to the bottom, it goes several up. And what I've got here is like, this is an example of one cortical column in, let's say, V1, you know, the very bottom of the hierarchy. At that level, that cortical column gets some of the input to process, okay? It gets a field of view of the space. At the bottom of the hierarchy, the field of view, and you can do this yourself, is about the size of your thumb at arm's length. So in V1, which is right here, the back of your head, you're only processing about the size of your thumbnail, but it's very highly detailed. I mean, you can read a piece of paper, right, at arm's length. So that's all that bottom part of the hierarchy is getting. As you go up, the field of view of the sensory input broadens. So as you go up the visual hierarchy, you get a broader field of view, but the detail is blurrier. You get less detail. And again, we'll send one more at the higher region of the hierarchy, and you just see it's blurry. The same thing. Broader, less detail. So the interesting thing about this is all of these columns, all of them, every point in the hierarchy, no matter what they're connected to, they're all doing the same things. They're all doing the same thing. They're trying to like resolve to an idea. Right? When we're like, I like to take the example of if you're inspecting an object and you don't know what it is, you dedicate all of your senses toward it, right? You explore the thing, you move around it, you look at it in all these different ways. You're moving your sensors at all the different levels of your hierarchy across an object and writing sensory input tied to locations in space into the synapses in your brain. That's how you learn objects, through sensory motor exploration. Of course, there's more to it to that. You know, there's a sleep cycle involved, but at a very basic level, that's what you're doing. So I'm trying to make it seem the hierarchy is definitely important, but it's not as important as we think it is. Okay, the hierarchy is like the purple stuff here. All of these cortical columns have massive amounts of lateral connections, like layer 2, 3, layer 5, layer 6. They all have these cortical connections that some of them will go huge areas across the brain and connect to some cortical column on the other side of the brain. Why is it doing that? Well, I think one of the reasons it's doing that is because if one of these cortical columns has an idea about what something is, and it's connected with all these parts all around the brain, all of them can then vote together. And then so if one part of your visual field, one cortical column dealing with part of visual field, has an idea about what an object is, it spreads like fire through the cortex. You know, it goes all over because there's all of these different lateral connections. It goes up the hierarchy, down, it goes all over the place. So you don't have to think, well, the object's going to form down at the bottom of the hierarchy and travel all the way up, or at the bottom and come down. It's very likely just whatever figures it out first transmits that to all of its neighbors that it's sharing its dendritic synapses with, or its axons with. So who cares about all this stuff, right? This is like all theory. And there's more to it. I mean, we're talking a lot about thalamus now. Next week I'm going to give a whole presentation about how the pulvinar thalamus could be involved in propagating error across cortex in some way. But what can we do right now? And especially in deep learning, because that's what everybody's doing. So we asked this question too, because honestly, we've we've been studying the brain and trying to figure this out for so long, and nobody's paid any attention. And so we're like, well, what could we do? And let's do something in deep learning. So we said, what is it in the brain that makes it really powerful? What is it that we could take from what we know about the brain and apply to these deep networks that Ravi was just talking about? And I think there's a few things, but the first, I'm only going to talk about one, and it's this idea of sparsity. So I didn't have a slide about this, and I kind of regret it now, because sparsity is really important in your brain. When I say sparse representations, I mean like when you think of your Aunt Mildred or whoever, when you think about somebody, there's a certain neural code, that comes on in your brain. You have neurons that represent that thought somehow. But no matter what you're thinking about, only about 2% of the neurons in your brain are ever active at any one time. So your brain keeps everything tamped down. No matter how much stimulus you're getting, no matter how bright the light is or how loud the sound is, your brain has a normalization function, and it keeps everything sparse. And the sparsity is actually important. So when you look at neural representations for objects, they're distributed across broad ranges of neocortex. They're not just localized in one place. You'll have the vocalization motor commands for how to say dog in one part of your brain, and you'll have the auditory recognition for hearing the word dog in another part of your brain. You'll have sensations for dog hair in another part of your brain. All those things come together to form your representation of what dog means to you, and it's all based on your sensory experience with dogs your whole life. That's your representation of dog. And it's all very sparse, and it's all very associative. So if you were to take your representation of dog out of your brain and put it somewhere, this wouldn't work between people, but within one person it would. If you could take your dog representation and your cat representation and compare them together, you would see that they would overlap in the places where both dogs and cats are furry mammals and have tails and have ears and breathe and are living things, right? But they would not overlap in the parts where dogs bark and cats meow and cats are finicky and dogs are overly emotional and whatever. So anyway, my point is we wrote this paper called How Could We Be So Dense? The Benefits of Using Sparse Representations, and this is all about how to take neural networks, standard sort of vanilla neural networks like convolutional neural nets, excuse me. So we took like MNIST and the Google Speech data set, some of the basic data sets that everybody goes and does machine learning stuff on. We took the best examples of standard convolutional neural networks for those networks, and we made them sparse. So there's a certain way you can apply sparsity that the brain does it. And so we made it sparse in that way. In a neural network where you've got layer, 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 and they can have thousands and thousands of units in those layers or hundreds or whatever, but they're all densely connected to the next. Every single neuron in every single layer in a standard deep learning network has a connection to every neuron in the layer before it. And there's a weight associated with that, and there's an activation function that decides whether that neuron is going to be active in the next stage or not. So what we're doing is basically cutting the majority of those entirely, because we know that you don't really need them. So there's been some deep learning studies. You could look up things like the lottery ticket hypothesis is one thing to look up, but where if you find the neural network and you already trained it, right, and it's really running well, you can go through the networks and zero out a majority of the weights, and it will still perform well. which is crazy, right? But it proves the point. There's a lot of stuff going on there that doesn't necessarily contribute to the accuracy of the model. And if we could find a way to apply that sparsity in a logical way that doesn't lose resolution of the system as it's trying to model whatever it's training on, then we're going to come out with deep networks that have a vast fraction of the computational cost and power usage when we're training them. So that's the focus that my company is on right now, is how can we make realistic deep learning networks and make them easy to make sparse, and so that they'll run much faster and with much less computational power required. You get an added bonus with this, because sparsity just gives you fault tolerance and noise tolerance for free. That's just the way neurons work. So, so this is the standard CNN, and then one where we applied sparsity to it. And then I just fed in MNIST, random MNIST with noise, and the sparsely connected one always does better with noise. And I did this because I expected it. If you think about neurons in your brain, you add noise to an image, you ignore the noise, right? The semantics of the image are still present in the neural activations, even with noise, and you can still pick that out.
Does that include adversarial noise?
Adverse, probably not, no. I don't know how you can fix that.
Okay.
Yeah, I don't know. You know, it might do better versus adversarial attacks, but we haven't done any research on it. Okay. Hadn't even thought about it. Okay, so there's a couple more slides about the future. This is something I'm very excited about. I think this is the future of AI, and I think it'll make, I think it'll change the playing field. So all of the GPUs that we use today to train deep learning networks are really efficient. They were built in a way, you know, by NVIDIA or whoever, to do this type of dense matrix calculation that's required for back propagation. And they're very good at that. But if we can, I'm saying the future is sparse computation, right? So we already can make these models sparse and prove that it takes fewer computations, less training time, etc. But that doesn't amount to anything until we have hardware that can take advantage of the sparse computations. So we are looking forward to developments in the neuromorphic hardware scene, which is really hopping right now. And what they're going to do is they're going to start making chips that have dense representations, are able to have dense representations. You can do this on GPUs, but it's just super inefficient. They're not meant to process data like brains, for sure. Brains are very, very distributed. So once these chips start hitting the market, 3 to 5 years, sometimes this decade, we're going to have, I think, neuromorphic chips that can handle sparse computations. This is going to level the playing field for the AI industry. So I think it's going to mean that many more AI startups will be able to get into the research business again, because right now it's very hard to do real AI research with real live models, with real data, because it takes such a long time. Like ridiculous amounts of time and compute and training, etc. That's why we have like the Googles and Amazons and Facebooks are all leading the charge in AI because they have all of the compute power. Once we get sparse computing on chips, this is going to level the playing field so that we can have the smaller shops and the smaller startups do some real AI research. So I'm really looking forward to this. Yes?
Are hardware companies actively working on that?
Definitely. I can tell you at least of one called RAIN Neuromorphics.
How do you spell it?
R-A-I-N. I know, you never know. Okay, last slide, and then I'll take questions and discuss. So I sure really believe in sparsity. I think that's going to make a big impact in deep learning, and I also think it's going to get us some attention because we're saying this is all brain inspired. The only reason we did this was just to prove that it means something. Brain research means something. So I think this is going to make a splash as the hardware appears, and hopefully we'll get some of the big companies doing AI research coming back and looking again at the brain and how does the brain compute and how can we create systems that are more like it. Deep learning has a lot of legs left. So I'm not saying deep learning is dead. You can, I swear, if you put your mind to it, you could do anything with deep learning if you have enough time and compute power. So there's going to be a whole swath of new applications, a whole new swath of innovations. People are like just digging through the math bucket right now. Let's like try, what can I do to optimize this? Like, what's the next big thing? And it is, it's like a huge toolbox full of functions. So I don't think though that deep learning is going to lead to strong AI or AGI. There are people in the field that do believe that, like Jan LeCun, Facebook AI. To some extent, Yoshua Bengio But I have never seen that. I don't think it's going to happen. Like I said, you need real neurons, or at least better neurons, and you need movement. You need to understand that time and space is sort of the construct upon which we build our simulation of the world, and the brain is a simulation that you're constantly running, essentially. So my company is going to keep researching brains, and if you want to keep up with what we're doing, subscribe to our YouTube channel, because we're live streaming on it right now. All right, so I'll take questions. Yeah?
How does sparse differ from pruning?
How's sparse different from pruning? So you could attempt to prune in order to make a representation sparse, but there's different methods you can use for pruning. So you have to decide which weights you want to prune, and that means you have to decide which ones are meaningful to the system. And that's a tricky thing to do, right? You don't want to prune weights that are contributing to the accuracy of the model. So there's several different mechanisms for pruning. What we do to try to apply sparsity is something different. We apply something called, well, in the brain speak, in our theory, it's called spatial pooling. And in machine learning speak, I would probably call it a k-winners take-all activation, okay? But with an additional level of homeostasis applied. So when you have a k-winner, so there's two different ways there's actually like 6 different types of sparsity. But the main ones that we're applying to deep learning is sparse weights and sparse activations. So the pruning would be, I think, pruning the weights, and then the activations are another way to apply sparsity. If you do random pruning, that's one way to do it, but it can degrade your model. So the way we do it is we activate, or excuse me, we cut all of the weights, like we zero out most of the weights up front, and that's just static. We leave it static throughout the whole training of the system. And we train the weights off of that, and then we activate the layers based on the k-winners take-all activation, which only allows a certain subset of the units in the layer to represent that input. Does that make sense? Okay. Yes?
I'm wondering like if this sparse computing like requires less data compared to the traditional.
So there's in the way we're applying it to deep learning, no, because we can't make deep learning better in that way. But in the way that it applies to your brain, absolutely. But it's not about the sparsity. That's not what makes it that way.
Yeah. So like my concern is, so basically, let's say, so the sparse computing is more like, let's say you develop a food processor to chop cauliflower, and the traditional deep learning is just you use a knife to chop it. But we still need the cauliflower, which I need the data to prepare a meal. So if it still requires the same amount of data, still doesn't solve the problem of Amazon, Facebook, and all the big giants are doing it because you don't have the cauliflower.
You know, the sparsity is not going to help the cauliflower. It won't reduce. It doesn't reduce the amount of training data that you need to push through it. It reduces the amount of training time it takes to push through it. So you're still going to need, as far as I understand it, the same amount of data to get the same results. Now, but again, that's not how your brain works. Your brain doesn't need lots and lots and lots of data. It has like one-shot learning, instantaneous learning. If you learn you can learn something once and never forget it again. But you know, that's a different type of learning entirely. Yeah. Yep.
Do you know specifically how that works? How the brain does it?
It's called Hebbian learning. There's a lot of different types of Hebbian learning throughout the brain. I don't think I can go into it right now, but it's a localized form of learning where there's like a post and a pre-synapse and either one can be reinforced. So that's how local learning works in cortex. Yeah.
Okay. I'll look it up.
Okay. Yeah.
So when you say sparse, I think sparse file system and a hash table. So the more buckets you have, the easier it's to look up. Are you saying that's the same concept or no?
The more buckets you have, the easier it is to look up. I'm not sure if that's the same concept. So you have to think of semantics. When you think about sparse representations, it helps to think about semantics. Every representation in your brain has semantic meaning. That's one of the things that we miss out in the ANN world, because if you take a representation out of an ANN, it doesn't mean anything, even to itself. It doesn't mean anything. If you take a representation in your brain, there's a semantic meaning to it. And if you take another representation, you should be able to compare them to tell how similar they are, right? And the sparseness is just, it opens up the playing field. So if you have a data structure that's 5 bits wide, you know, and you only put, and you put a bit, and you could put a bit in each one of them, that's 5 to the power of 2. But as you make that thing really big, there's a sweet spot, right? Around, you know, around several thousand units, where you computationally can represent anything in the known universe, right? But just by turning these bits on and off. You have the space in your neural representations to represent an infinite, essentially infinite amount of things. That's why you can always continue to learn. Okay? Yeah.
You mentioned that in your brain you can compare the cat and dog networks. Does that mean that the AGI might require thousands and thousands of different networks all working together?
No. So the way I see network, I think a better word for that would be a tractor. If you're familiar with the term, I like to think of neural representations in the brain as an attractor. An attractor is a pattern that has a sort of an ability to self-complete if you invoke a portion of it. And so I like to think of neural representations like cat as an attractor that's distributed throughout your brain. This is just me, okay? This isn't like official Numenta theory. I like to talk about brains. But so if you reach into a box and you want to figure out what it is, and you feel something that feels like a cat, only the part of cortex that's responding to these part of your fingers that are touching the cat are making that decision, are making that call as they're touching the thing. That invokes an attractor throughout the brain, right? That thing that's like, oh, it's fuzzy, it might be a cat or a dog, and then the cat pushes up against your hand and you're like, that's a cat, right? That's the type of representation. It's sparse because you don't have to store a lot of data just to say something is furry or fuzzy or not. You don't have to remember every single hair that you touch when you're petting an animal. You know? So I think that's the way I like to think about it. And if you think about it that way, the cat's an attractor, the dog's an attractor, where they overlap or there's similarities, right? You can jump. I mean, like, the way you represent data in your brain is just like a web of interconnected things. Like you can just, the train of thought, you can just carry it from one thought to another thought, to another thought, to another thought. You're invoking attractors, exploring the space a little, grabbing a subset of it, invoking another attractor, exploring the space a little, invoking another attractor. That's how your thought process is going through, sort of keep holding things in your brain as you like think through ideas, for example. This most likely happens in prefrontal cortex. That's like your working memory.
It's not linear.
It's not linear, no, definitely not. There's not much in your brain that's linear. Yeah.
I have too many questions, but
well, I don't mind staying. I don't know if Jim's going to kick us out at some point.
So you said in the beginning how important space and time is for intelligence. How does that work with an AGI system? Like if it's embedded on a chip?
Well, like, again, there is no AGI system in computers today, period. It doesn't work. We only know this from studying biology. And a lot of this is theory. You know, we're not certain. There's a lot of experiments that point, experiments and evidence that point toward this, but we don't really know.
So hypothetically, that if you can create some sort of AGI, it doesn't have to necessarily propagate through space.
I don't think you can ever do that. No, not physical space. It has to be able to move. I don't think. So here's the thing.
It could be virtual movement.
It could be virtual movement. You could make a smart web crawler, for example. You could give it. It has an environment. It starts at a URL, and then it scans a page and it looks for links. Its movement could be choosing a link to go next. You know, that could be a movement. That's a movement through the internet space. So there's lots of ways you might define moving through space. It doesn't have to be bound to physics. It doesn't have to be bound to simulation of physics. All you need is an environment that you can move through. You know, and moving, I just mean change your perspective. You have to have a sensor that's receiving information in some environment and the ability to change its perspective of the environment. That's the first thing you need to start being intelligent.
That could be done dynamically on a case-by-case basis. But you can do it with 3 stones.
3 stones? Okay. Usually,
I don't know.
okay, okay. Yeah.
Do you have, as far as Numenta, do you have anything applied yet on the motion and the location cell aspect?
So yeah, actually, on the grid cell part, we have a paper called How Does the Neocortex Create a Sensory Motor Model of the World? I think that's the paper. And so actually go to numenta.com/papers and you'll see all of them. And the one that has like hands and fingers touching things, that's the one. Because we mocked out a cortical column. Well, I won't bring it up, but you saw the diagram of a cortical column. We think that like certain layers representing this type of space and other layers representing space in this way, and this is how they're communicating. And together, you have to inject movement into the system somehow. Like in your brain, your cortex is generating motor output everywhere in the cortex, like your whole cortex, which has confused neuroscientists for decades. But that motor output is like it's your predicted state of the world. It's where you think you're going to be, in the next moment. And we don't have we don't really know how that works. Like nobody knows how it works. Yeah.
Along that line, I read a book a while ago by Lisa Barrett. Have you never heard of her?
Lisa Feldman Barrett. Yes.
And there was a test that they had the brain map, and the hypothesis was you're going to show a snake come in the room, the visual part would go hop, and then your arm would get ready to act.
Yeah.
And they found that the arm fired up.
Yeah.
Before the visual part.
Absolutely.
Has that been tested or?
Well, yeah. So there's artifacts of evolution in your genes that that express themselves to create your brain, essentially. Some of these artifacts are really, really old and ancient. So you might have something genetically encoded into some part of your subcortical structure to recognize something that looks vaguely like a snake, right? And would invoke some fear response. Everybody's afraid of snakes and spiders.
But before the visual.
Before the cortex even gets involved, it's almost a reflex, subcortical short circuit.
They did one more little addition on another one. They put the snake behind the door. And arm reacted as it gets ready, and the snake hadn't gotten in the room yet. Now that was in the book, and I would be very interested to know if that's been researched or looked at, because it means there's some kind of sensory input that human beings have that we react to, which will affect everything that you're testing.
Well, I don't know. I wouldn't take it like that.
It's this unknown piece.
Your brain is constantly pattern matching, not just in the neocortex, but in all other parts of your brains. It's trying to resolve to certain patterns. And if when sensory input comes in, it makes a stop in the thalamus before it projects all the way out to cortex.
How does that brain get the input with the snake behind the door?
How do you know
like I said,
the snake in your car right now?
What?
How do you know what there is no snake in your car right now?
I think his point is just there's some stimulus that short circuits the cortex and gets an immediate motion response without the cortex being involved. Because I was saying that motor outputs everywhere in cortex. Your cortex can't control everything. Try and hold your breath until you die. You can't. I mean, because there's subcortical processes that will take over. So that's an example of something like that, very primal, some type of fear of dangerous reptile that could be expressing itself in your genes at a very low level. Any other?
Reinforcement learning, can that not be applied to AGI? Just general
So reinforcement learning has one great thing going for it. It allows you to get movement into the loop, but you still have to have this loss function so model-free reinforcement learning I don't think will work. I think you have to have a model of reality, and perhaps this is a way forward with something more like the brain. If we can get a reinforcement learning system to have agency in some environment and build a model based upon that. The tricky thing is, and this is again sort of me speculating about this, I think the tricky thing when you try and do that is that the model itself has to generate something that is causal to movement. And that's the tricky thing. If you're going to take deliberate action in the world, planned action, something that comes from an object representation of cortex. So your cortex doesn't just have models of every object, it has models of all the movements and interactions that you take with those objects, right? The way you model objects very closely tied with how you interact with them. So the model needs to be able to contribute to the strategy of the reinforcement learning system. I don't know how to do that. Yes?
Do you have any little kids you work with?
I have 2 kids.
Yeah, so it's like they have a bunch of blocks. I bet you buy them lots of interesting cheap blocks and sticks.
Yeah, it's really interesting watching children learn when you're thinking about the brain all the time, for sure. And a couple of tips that I got from this. If you're trying to learn something, any way that you can incorporate movement into the learning is helpful. No matter what, if it seems silly, like when people tell you to just take notes for no reason, take notes for no reason. It's helpful. Even if you just throw them away on your way out the door. Just the act of moving, during that episodic memory, it's a reinforcement of what's happening at the time, and you're more likely to remember it if you've got more sensory involvement and more motor involvement in the situation.
So when you say that the brain uses very sparse computing, let's say, what happens to the other parts of the brain that are not used at that time?
So think about neurons like this. A neuron, one single neuron means absolutely nothing. You could take a neuron out of the brain and it will never affect anything. A neuron will fire, and if you're just looking at a neuron firing as you're watching a brain, it's completely random patterns. Like there's no way you can associate that neuron with anything. You have to look at the brain as a population of neurons all the time. It has no meaning unless you look at the entire population of neurons. Does that make sense? I don't know if I answered the question though.
Maybe a related question, that if you have those chips that use sparse computing, does that work in a similar way, like you're only using 10% of that chip?
Well, sort of, but you're not really just using 2% of your brain. You're representing something with 2% of your brain. The simulation is vast, okay? All of those neurons are used for something. You might not have thought about that book by Kant that you read 8 years ago, but it's in there somewhere. You have thoughts about it somewhere. Maybe you haven't exercised that population of neurons recently, but you could probably figure out a way to invoke it in your mind. Those neurons aren't wasted. They're used in all of the representations. Every neuron could be used in thousands of different representations, right? So it's not being wasted, it's just got a low level of activity. The simulation has huge memory banks. What's actually lighting up in the simulation is just an indication of what's currently active.
Would that be whatever enters your conscious mind?
That's a tricky question. So it depends. And I don't know if I want to get into consciousness right now, because I could talk for another hour, but I probably shouldn't.
I was going to ask about mindfulness, but I don't think that we'd be here for a long time.
I can talk to you later. I do mindfulness meditation. I think it helps. Yeah.
You've been talking about human brains or mammal brains. Have you been actually looking into different type of brains? Is there different branches in the evolution?
There's definitely different branches. So I think other interesting brains, I think bird brains are interesting, mollusk brains, like cuttlefish, octopus are very smart. Dolphins, whales are very smart, but we don't study them. I think it's much, much easier to study primates, I think, because neuroscientists have a history of studying them. Like most of the brain studies are on mice or macaque monkeys, or pigs sometimes. Yes?
When you started this evening asking about what is intelligence, there was some interesting research recently released from Harvard about single-cell organisms called Stentor-Rosselli, and they get to make a choice when things irritate them on which direction they move themselves.
Yeah, yeah. So similar to what I was talking about,
the
right?
primordial stuff.
Yeah, I mean, where do you draw the line?
Yeah.
So I do think that there's certainly a difference between intelligence and consciousness. I think that both of them have a spectrum involved. And I think that in some cases you can be one without the other.
I think a lot of people think single-cell organisms don't really have much of anything going on in them.
And people also think they're not conscious. Maybe they are. I mean, I don't know. I mean, the more I learn about the brain, the more questions I have about these things. I mean, maybe plants are conscious. Maybe rocks are conscious. I don't actually think rocks are conscious. But there is like panpsychism, right? That people do think everything's conscious. But I think it's sort of ridiculous. Okay.
I think maybe you should try talking
To rocks?
No, but doing things. Try talking regularly to one favorite shrub.
Yeah.
That can flower.
Yeah. I wouldn't be surprised, honestly.
Flowers more.
There's definitely studies on plants where they will play different types of music for different plants, and it certainly has an effect. Plants don't like death metal. And maybe it's because of vibrational effects, or maybe not. There's also studies that if you put a seed in earth, even without a sense of gravity, and you play the sound of water, the seed will grow towards the sound of water. That's crazy. How does that? Nobody knows how that works, but apparently that's the thing.
Big thing.
Yeah, how does that? There's lots of unanswered questions. So, okay. Any last questions? Thanks, you guys, everybody, for you can stick around. I'll talk to you. Thanks for joining. Thanks everybody online too. No, we don't go down
Well, you have a bit more.
No, we don't do studies like that. We really still do trying to understand the concepts of intelligence and researching mechanisms. And right now we're really focusing on written because we think that's going to help us understand how positive But as far as nature versus nurture and genetic effects, we don't ever really go to that level. Because I mean, it opens up a whole new example. There's so many more.
I'm not sure what
there.
first would
We're really focusing on is just one
Just
form
the
of computation.
basic principles of
And so anything that is involved in that's what we do. And right now we're really studying bounds and how it contributes to the representation of the environment. Bounds involved between every layer of the hierarchy, both bounds, non-bounds, non-bounds. And
and say, okay, over now, we did a job explaining the institution behind it.
right. Somewhere there's some innate capabilities baked into our computational brain structures. We're not trying to find those. We're trying to find out how the emergent architecture. So after the brain basically has grown, that it's there and we can look at it and we can figure out how it works. And to some extent, we look at the evolution of the brain and the growth of the brain from like embryo up. Because that teaches us just what structures emerge, where those structures come from, like as they grow or whatever. And then, like I said, the evolution informs us about
That's simple explanation. I've gotten.
I think this is what brings me now.
So I have an unrelated.
But that's not what drove me ever research, honestly. I read that paper.
So am I
We weren't calling the neocortex isocortex. So I read this paper and it was all about how the neocortex isn't really new. Neo means new part. The neocortex isn't new. It was around all the way 500 million years ago. It was part of the old brain of the vertebrates, and it was called isocortex. And just wanted to move to isocortex nowadays.
It's a very common thing.
That's a curveball.
And it's very common. It's like you see those kinds of things all over the place. But if you have to relate to the partner, it is time to do it.
Sure. And we have a form.
So for a deep learning algorithm exposed to that pattern.
Yeah, go to
You have no clue.
Numenta.org.
Dumping your, you'd be telling the people.
We have a
In the trash can, or,
You'll
yeah,
find it.
yeah.
But,
Search
but,
for Numenta.
so I
Yeah.
thought about it when I thought about it before, and then I thought it actually says how much we rely on context without even realizing we are, especially communicating.
Yeah,
Honestly,
Yeah,
I don't
at one
have
point,
time
I
to work
remember we
individually,
had that.
so I get requests for that, and
I
I have
remember
to turn it
thinking,
down.
you know,
When I
I've
get
seen
what
a
to do
certain
is
type
all
of
of our
science
educational
that
materials, I've got a
never
whole
use
series of videos
English
about
language
how
like
technology,
precise.
like
So, to where it was just no question, we could say, oh, I think
It's also, there's this version that you have of even reference.
Using
What
the word,
there's
yeah.
a new point. It's like, oh, if you put this damn science say nothing but human waste into it.
And the
Not
torture
just
side.
it's not insulting. It's
Yes.
but on a subconscious level, it's not just everybody knows it.
Yeah.
That's my theory.
Yeah.
It's both.
Good, I wasn't even around, I've been here for 8 years.
But it comes back to the rules. It's an example of how
And it was all like, by the time I got there.
Yeah.
Most AI would get that totally wrong.
So
Right,
there's
right.
big science and more on there.
Right.
Science stuff. Check it out. Well, you know where, I would give you this, but you probably already know. Yeah, no problem. But yeah, check out more. Yeah, I might just read this more because honestly, it's also questions on
Yeah.
answer questions for me. I think that our form is pretty well educated on this stuff. A lot of these people know more
Yeah.
about.
I want to say if I did, I know a few parts of it, I haven't seen.
It's got
No, I don't. Yeah.
We don't need to go anymore.
The answer is drones, but they're throwing all this money.
Cool, yeah.
Which is why Sharon.
Don't put any points, yeah.
We are.
Yeah, did you guys at least find it? Did you come out for me and found a place to get food?
We did a really early light dinner.
Perfect.
That worked good.
Yeah.
Yeah, I have a series of
That's true.
Which is why we gotta get.
and that was from the last one about hired.
Oh, don't worry about it.
But we also
And-
gotta
and
get.
it-
We appreciate getting it.
Yeah, and the main thing is, it'll show you, so that, I think, I remember the numbers, but it's somewhere in the, I think the 140, the 160, the total amount that's in the fund. And the main thing is the back find.
So basically,
So there's one idiosyncratic question about plants.
so I think you need a sense of self. Okay, you need to have a, I don't know if it's emotional self or not. There's a
It is
difference
exactly
between sense of physical self.
And then if you look.
This is tricky to figure out, but I think that you need to know the boundary between your body and the environment. And so initially, it's your awareness that what you move in your body affects the environment and makes it back from that motion. You need to have the ability to move a body and for the body to come back from the movement. And that's and you think about thought as God is also moving process. So yeah. So imagine the little fish, years ago, the way that it's navigating, it's considering to move away from something or to something. Think about throwing a baseball. Now throw a baseball. The neurons like fire when you think about throwing a baseball. It attacks the neurons. It's just
Right,
being
from
somewhere
the
that says yes, you need to action.
It also is being.
But one of the key things
Hopefully
that really
it's better,
is
yeah.
conceptual space is just the
It's in a
instruction.
CD.
So when you think about ideas like kinship
It really
or democracy, your brain has a representation of ideas, something like that is in the same way that it represents physical objects. So we navigate physical space with sensors, and we navigate abstract ideas through our mind by moving through abstract space. That's why we always use metaphors and say everything is simple to the real world, because all of our learning is referencing the process. Like even like I said, at the higher levels of the hierarchy, they're even getting
Right.
And not all the way to the top, like you have construct together, but that is just a conglomeration of sensory, a bunch of different sensory inputs. So every symbol that we have in our mind is grounded into every experience that we've ever linked to that symbol. Because it's that complicated. So in a way, this blows people away too. Like if you took an agent and it had a sensor set like a spider leg or something, and you said, learn this environment. And then you're like, okay, the spider knows this environment, like if it starts to branch out or whatever, and then it starts learning, you give it some sentence. So it's got a representation of space.
Exactly.
If you move the spider to another place and told it to explore, it would take what it's learned there, and relearn how to move. We're just
We're talking about it. We're talking about it.
if you took that agent, modeled the world out of the agent, put it into the computer, right? Unless you put it in the exact same body. So you can't transfer these like transfer, right? You can't transfer what you've learned in one environment to anything which is so like that's things that's really hard to understand. You realize that you lose all of that, it's like there's nothing you can take over from one place to another. But this is a problem in start learning too. They call it like catastrophic forgetting. You can't take or transfer learning. There's big problems with transfer learning. You learn this space, you can move on to that space.
We were on the book. But when she read,
What's a mule
no problem.
from what's a horse?
And it was like that. She had a great first grade teacher.
Yeah.
Just all about how great it developed.
Right.
The teacher recognized how to teach her. But that was, it's like, it's very memorable to us.
Yeah.
She went from 1 year from.
But intelligence is something, it's like they don't know self.
The story.
Well,
So one of the, our boys are language and then he and I end up reading together, and I had read some of the earlier, but we know one or two of the books in series.
It's very primitive.
For self, yeah.
And
Yeah.
we'd be listening.
You don't need much to be conscious.
And they'd be all in his car. And
Yeah.
and I'm there with her.
You do
Can you
something,
believe
you
that?
see that something happens,
And the
but
voice
you
is
know
heard
that
any
when I
of
do
it.
something,
And
I
that's
make a
what
difference in the world, that's about it.
Yeah.
But
Yeah,
yes.
it's
You don't think about any, like,
Really good friends
think
across
about
the
anything
street.
beyond, just your own self.
Right.
Yeah. This will blow your mind.
Female half.
So so self is important when you think about consciousness, but when you try and inspect thought, and you looked like this is a meditation, one of the things that you always try and do is observe the thinker, right? At some point, you look back and try to observe the thinker, and inevitably you're left with nothing. You can't observe the thinker because there's no thinker in the simulation. The simulation is the thinker, right? That's
Oh, cool.
that's
Tell me
one
all
of the
about
keys.
it,
It's so
yeah.
simple.
Yeah,
and
I just
everyone
wanted to
is-
remind you that that's
You
something.
can't find
You have
yourself
to-
if you're looking for it consciously.
Yes.
It's not there. There is no self. It's fucked up. What kind?
And then maybe we'll grab those with students and take them.
No. No.
Oh, okay. But, and she's still doing the acting and the managing and running the IT and the whole nine yards?
Yeah, sensory deprivation.
Oh, whatever.
Yeah, so I've done flow tanks,
The office, right?
closed decisions.
She's actually.
But the interesting thing with meditation is like your meditation sort of short circuits your brain too, because you've got this constant loop where you're constantly predicting what's happening all the time. And meditation is you're practicing just just let everything happen. Don't try and match it to the objects that you know. Don't try and process that on the car. Just let the vibrations come, right? Just let everything go. Don't predict anything. And that does enter you into an interesting state of mind where in some ways patterns emerge that don't necessarily emerge otherwise. I think that's what's useful. Cool. Thanks guys for coming.
Yeah, thank you. It was really great.
Nice to meet you. Do you want to part?
Yeah.
No, we don't do any chip stuff. This brain neuromorphics thing, they just come to our company and talk to us about it. Got us all excited about it.
Oh.
It's in the city as well. Yeah.
So what's your company's product?
We don't have a product. We're a research company. Yeah, so we're not trying to sell anything.
So like it's funded by university?
Well, it was, so do you remember the Palm Pilot and the Trio? So the Trio was the first smartphone that was invented by Jeff Hawkins. Jeff Hawkins started Palm and Handspring. He only did that because he wanted to do brain science, brain research. So after he made enough money from those ventures, he founded a neuroscience research company, and then Numenta to continue the research. So we're privately funded by a rich
Oh, so
it's all funded by Japanese.
Well, I wouldn't say all. There's a board of directors. I know there's other people that have invested, but for the most part, it's money from all. And the vision is to understand how the brain works. I mean, it seems kind of silly and altruistic.
Actually, not silly, but I can tell how much money it takes.
Yeah. So
and how long?
I don't know what's going to happen with the company. It's been around since 2005. I've been there for 8 years. We're still trying to get attention from the rest of the AI community because our work doesn't have profitable applications right now. Nobody works with it. Nobody's interested in it. That's the problem.
Yeah, I'm actually very interested.
Yeah.
It's my personal interest. Actually, I have a data science background.
Well, join our forum because there are people like you who are in our forum. People who are interested in this because we want to understand how brains work and how intelligence works. That's our bread and butter. Like we have a really nice community of people. Some of them are probably still watching and chatting over there. I see them in the chat.
Awesome. Yeah. I hope this continue to thrive and stuff.
Well, thank you.
Basically, this is the first company I ever known to basically don't have any actual products. And
the people don't usually like that in Silicon Valley.
At first I thought you guys are working towards that chip thing, and I was kind of curious.
Well, if that happens, that's great for us. Whatever, any types of chips that come out that enable sparse computing or neuromorphic abilities, because we need chips that because we need synapses that change with time. You can't do that in silicon. So we need chips where you can model that change. Like the values of the chips are changing over time. Yes, it's analog. We need an analog processor.
Now it's just discretized.
And that's what brain neuromorphics has. It's an analog distributed processor. It's brilliant. It's really cool. I have a video about it. It's highly people.
Yeah, thanks.
Yeah, you're welcome. Nice to meet you guys.
I'm curious, what is your goal for coming and talking to us?
I'm just trying to spread our theory, really. Jim's talked to us over the years for a while, asking is anything developing. I think he's interested in what we've been doing. We've been around for so long. And so he asks us every 5 years if we want to come, advise the school in one way or another. So we just asked if we wanted to talk.
People don't research.
So the company has less than 15 people?
Yeah.
Like right now? That's pretty much Are you hiring right now?
Yeah. Machine learning, unfortunately.
That's not unfortunate.
Okay, good. So yes, go to the website. I'll give you a show. Yeah, /careers, and there's machine learning positions, research positions.
So I used to work at Google Green.
Yeah.
I'm at a startup now, and I'll probably be there for the foreseeable future. That said, I'm interested in learning more about the company where you're at today. Maybe developing a conversation. I don't know where I'll be at in 4 years.
That sounds great. You know, we're always looking for smart people, especially people who are really interested in brains and have an inkling about how they're different than like deep networks. I find it very hard to explain to some of the machine learning community how what we're doing is very different than what they're doing.
I think it's different, and yet it's conceivable that some of the functionality you're looking for could be achieved by what falls under the umbrella. What do you even define as deep learning and not deep learning?
Yeah. Well, like I said, I think that like if you have a narrow goal that's very well specified and defined, you can find a solution using an ANN to do it.
Yeah. A lot of data, a lot of computing.
Yeah. But we really want something general. We're looking for that. You know, we're looking for the pie in the sky general intelligence.
Sure. I asked sort of a basic question about sparsity and adversarial examples.
Yeah.
In a podcast, I heard Jeff recently cite a result saying that sparse representations are actually more robust than adversarial ones.
Maybe he's right. I don't know.
And then I looked at Sutai's paper.
Yeah.
And it actually cites that original.
Oh, well, perfect. Okay,
Yeah.
then I can say yes for
Yeah. So then
cool.
it's like it's like
The adversarial noise in particular.
Adversarial. Well, yeah.
That would make
Adversarial
sense.
examples.
Okay. Because it's better with noise. It would make sense that it would improve adversarial noise.
But it also begs the question: if sparsity is enough to get that sort of robustness, sparsity is compatible with most deep learning methods, backpropagation, etc.
Yeah.
So, like, is that still a piece of evidence to say that deep learning is
That might be. But I mean, we're not pushing on that. We're just honestly, we think that if we can find a way to improve how fast you can run today's deep networks, that we're going to make a bigger impact than if we just continue doing raw research. Because I mean, that's still like you're looking pretty far ahead as far as products go and making money when you're just doing raw research. We're hoping we can show some applications that will give us some attention.
Sure. Attention from the research community. Deep learning.
Yeah. From people doing deep learning and training models and wanting to do them cheaper, wanting to train them cheaper.
Hey Matt, I'm gonna jump in real fast. I'm with the university. I'm actually a money's guy. I don't know if you have a card with you.
I do.
Great. I'll just reach out to you in the sense that I'm in the physical biological sciences division. And we've got, in fact, I saw one of our astronomers here tonight. We've got people doing the AI, machine learning, the neuroscience. And, you know, depending on kind of where you guys are looking for, you know, whether we do any collaboration or maybe have you present to one of our graduate student seminars.
Yeah.
Real fast. So we have some faculty working on growing brain cells, artificial brain cells.
Really?
Yeah, and that's still different from what all these other guys are doing, right?
Yeah, that's weird.
Yeah, so I'm gonna reach out to I know some of them and point them to your guys. And right now, Numenta is mostly research, like you said, around the brain.
Yeah.
But it also sounds like you're looking at
we're
can you make some.
Yeah, so for the past, several years, we were just neuroscience research, and recently we were like, let's test the waters with deep learning, see what we can get out of it.
Right.
So we've got 3 engineers, 3 people working on that.
Okay.
But
8 a.m. to
4 or 5 actually.
Well, and so
it's just me and Jeff and another neuroscientist, Florian Vivek, who works for us, who's doing the research, neuroscience research.
Okay. Well, and so like one of our faculty members is working on a new artificial intelligence initiative that has to do with bringing industry and research and students together. I didn't mean to interrupt. So yeah, maybe there'll be some synergy we could work on there. Hey, real fascinating. Thank you.
Thanks, Lemia.
Yeah, likewise.
Take care.
Hey, thinking about the smart animal or animals of consciousness, right? Or the intelligent.
It's most like
some of the things, and maybe this, I think this has been known for a while, but I didn't understand it. But the fact that dog-like animals like wolves, their pack behavior, but they will divide up. It's like a coach playing a football game.
Yeah.
And they will send in a decoy
Right.
to pull up a dog.
And how much of that is innate?
Right,
and
right.
How much is actual communication?
But how, yeah, I mean, the innate part is, except that if it was innate, then we'd all be together, and we'd all know the same stuff. But how am I gonna tell you to do this and I'm gonna do that?
I think it's a combination, you know, dogs communicate with each other.
Yeah, oh, they do, but I guess in my mind, communication is
But
would
if
be
it's
another
just-
indicator.
What if it's as simple as there being an urge to divide and conquer, just as simple as that, and then the dogs are just like, you're gonna.
Sure, yeah,
all
that's
you
what
need
you're
is
saying.
a little nudge
Right.
to
And,
execute
and I
your
think
urge.
about sports again, you know, if you see your teammates are going this way,
Yeah.
you know.
There's an instinct, you know, you're like, I know what he's doing.
Yeah.
We've
Well,
been doing this for
when
10
the
years.
gentleman was asking about the snakes, and I think he was trying to say this to you, and you hit on this in terms of how our brain processes, right?
Mhm.
And all the senses. He was implying that there was even an early detection somehow physiologically with that individual and what they heard outside the door when the snake was not even in the room yet.
Yeah, I don't know, I didn't get that last part.
Yeah, I think that's what he was, because he said the arm was getting ready. Well,
Because you heard a snake, or how, if you're not perceiving it, I don't understand what you're saying.
well, I think what he was trying to say was that it wasn't no longer the visual perception, because first that was what it was about. But that even without the visual perception, we all know, I mean, we have all different senses, right?
You're a rattlesnake, you're gonna.
Right.
You're not gonna think about
Oh, and I
it.
found myself thinking about, like you said, if this, you called it when something's an attractor, and I loved your example about the cat in the box. Right?
Yeah.
Because that's true, all those things are firing.
Yeah.
And so I'm an animal lover, but let's say I had an aversion to cats. And I felt the fur, and I got some of these, and then I got another indicator of cat. But maybe it popped this attract, you know, that had negatives, right? I may be pulling my hand and saying, that's a goddamn cat. Yeah.
Yeah,
Hey,
your experience with a cat is different. from
Exactly.
everyone else's.
Well, a real pleasure.
Thank you.
Take care.
Oh wow, there's still. Hey guys, thanks for sticking around. I'm gonna shut it down now. I think you guys can still hang out and chat if you want to, but I need to get home. Thanks for watching.
Thank you.
Take care.